Hey guys, welcome to day 3 of our build a game series with Rust, and thank you guys for joining again today. Really appreciate the commitment to learning together as we began from the first day 1, day 2, and now today is day 3. So thank you guys for joining. So yeah, just wanted to say that, and for all of you that have subscribed also, I appreciate it. Thank you for the likes, thank you for the subscriptions. Really appreciate that. So let's get into today's activity as soon as possible. um yeah, so let's do that. Let's go. Time to begin. So let me share my screen as I always do when we get started as well. Just a minute. Okay. All right, we set. All right, just a bit of delay on that aspect. Sorry about that. Yeah, we're back now. Okay, so we're going to continue from where we stopped yesterday, basically. So yesterday we did a lot, much more than normal. We started with everything we wanted to do, and we continued by taking a look at lighting. We did a bit on lighting. We did a bit on um, using things like tone mapping and bloom, which controlled the flare on the object where we actually added the lighting to. So we did a lot on those aspects, and we also did other things regarding um what aspect was that? So we did a lot on transitions, translations, transformations, basically transformations, and also on other things like um rotation too. Yeah, and we check some examples and be able to like make that happen. So today we are going to be looking at a bit more complex stuff. So yesterday I said I was going to make some things available to us, which I was not able to get like some of them. So I had like, just excuse me on that aspect. But then we are going to try getting it together today. And so what I said I wanted to do yesterday or get yesterday was to get the for the examples which we want to work with, which was working with the sprite animations and the sprite sheets. So we are going to be working with animations and sheets today. So we are working with sprite animations and sprite sheet and looking at how they work and a bit of 3D components, right? So the first thing that was expected of me was supposed to be the sprite animations. Let me just show you what I mean so you can understand. So this is basically what we needed. So if I move this now, left arrow, right arrow, you can see the animation for the sprite. So if I move, continue pressing the keys, you can see that it keeps moving. So this is what we are supposed to do today. Reason is because, like I said, we are building a game, right? So we need to understand all the aspect of a game. So that's exactly what we are trying to do. And looking at this code, we should be familiar with this. If you've joined the first day and the second day of this series, you should be aware and familiar with what we have here. So basically, two things are going to happen here. We need the image itself, the sprite, right? So we need that as an asset, and that's what we are going to use. That's expected, right? Based on what we've done so far. So we need that as an asset, and that is what we have here. Textures, RPG, cars, Gabe, I do run. That's exactly what we needed. So now I'm going to do something here. I'm going to go to the official GitHub account, right? And let's go and get this library. So I'm going to zoom in so you guys can see what I'm trying to do. So we're going to get the textures, right? Not the textures directly. We are going to load that and we're going to go to the examples because that's where we want to get our assets from. So go to the examples, go to 2D because we're working with 2D examples. We're going to go to the sprite animation, which is this guy. But in this place, we need the assets, right? We want the asset. And if you look at this, we want the asset from textures and RPG. So we look for textures here, right? I'm just showing you guys so that if you want to pick it, you can also make use of it because there's no need for me pushing this into a separate repo. Reason is because we really don't need it to be different, right? So what do I mean by that? Excuse me, guys. So we really don't need this to be a separate repo because I'm using this example. So I'm trying not to put it on another repository entirely. So we are going to be making use of the actual one that I'm working with currently, which is this Bevy's repository. So what I'm going to do is just to get that sprite or image out of it. And you can see the image is RPG, textures. We're already in textures. We need to go to RPG. So then we need to go to cars, then Gabe idle run. So cars, then Gabe. Like I can see there's a lot of assets that we can just pick from here. Gabe idle run. And then if you go to this, we can click on this and we should see the actual sprite here. Now you can see this is a lot. This is just a series of image. Like if you look at it this way, you see that it's a series of image. So we should be able to download the raw file from here. So I can call it Gabe idle run, right, which is actually the name, and save it. I'll just save it on my downloads for now. Gabe idle run the png because it's a png file. So I'm going to copy that png file and copy it into this folder here, right, which is exactly what we want to implement here. So I'm going to copy that. I'm going to go to my download. Shouldn't be showing this, yeah, but yeah, no problem. There's nothing here that, no, where is it, did I download it to the right place? Yeah, I think I did. So let me search for Gabe idle run. Yeah, this. So I'm going to copy this, copy this, and I'm going to go here and I'm going to paste this. I'm not going to paste it directly into this place, or basically let's just paste it there, right? So let's create a directory, call it assets, and paste it here. So I'm not making this into a repo like I said, that will come eventually. So I'm going to rename this to Gabe idle run all underscore. So go back to display. I'm going to close this now. So go back here, you can see this Gabe idle run .png. Perfect. So we need to this place. We are going to the okay, for now we need, for this first one, for the other example we are going to need, I think it's the same sprite, I'm not entirely sure, let me check it just to be sure. So I'm going to go to the new tab I created. So the one we just worked with, which is the sprite animation, we've already seen the sprite. Then we are going to see the sprite for this other one, which should be, if I'm not mistaken, yeah, the same thing. So we don't need to download another one. It's basically the same sprite. So now let's go back to the animation first of all. The reason why I'm kickstarting this with just the example is because we've talked about a lot of things yesterday. So we talked about textures, colors. Let me show you guys what we did yesterday before I start today's one fully. So for those that were not here yesterday, we were able to do this yesterday. We were able to run this application yesterday. So we're able to run this and we're able to create more like of different shapes, right? Created an app more like a game with text. We understood what that was: the text, rotations, translations, and this bloom effect to give you like this light source, right? Coming, being on, like rendering itself one on top of each other, the circle on top of the rectangle, the polygon on top of the cycle, right? So everything just rendering itself, because you can see the sun doesn't go over the polygon, it goes behind it, and then you can see the light source following it around and reflecting on the surface, whereby it is actually in proximity with. So you can see when it gets here, it becomes brighter. When it goes here, it retains the light source of the polygon and it gets brighter at the end here, and it goes back again and gets brighter. It lightens up this place. So it is a very, very locational way, right? So all of these things we didn't do manually because Bevy already handles most of it for us. So we didn't need to do it manually, which is one of the very impressive things about what we are trying to implement here. But that aside, we understand what is happening here, right? So what we can do next is, I'm going to close this because that was our task for yesterday, and I'm sure we've been able to do that yesterday. So going back to today's implementation, because we're trying to rush up things, we want to do a lot of things and still enter into the 3D animations, right? That is one of our major focus for today, going into 3D. So we need to make sure that we also process that aspect. So we are trying to work with the 3D as well. So let's start with the sprites initially, and then we move from there. So going back to the actual code, we have the Gabe ID run, which is just a sprite. And if I zoom in, I think I should be able to zoom in. Yeah. Let's zoom in and see. So this is just, you can see the movement. So let me talk about the sprite. You can see this is the idleness, this is the first movement. So this is a sprite. So basically what we are trying to do here is we are trying to render for each time we move our keys, we are just swapping in one of the image for the other to simulate movement. So it's just like motion graphics whereby everything is a still frame. So in this case, this is also a still frame. This, you can split this here, split this here, split this. So if I'm to copy this file, for instance, let's say I copy this file and I go back here just to show you guys what I mean. I can create this, and that was what we did yesterday. So we did day 2, lighting, meshes, applying transformations. So today is day 3. Let's do something simple, something else entirely. Now you can see we adding this now. We added the image, right? So it's rendered, it's been rendered here and automatically being added. So we have the game idorun.png, which is our file here, right? And so that means I do not like things being out of place. Sorry about that. I need to put it in place. So we have this, right? This is us. So what we could do here is we could change this and ensure that, okay, this is a still frame, right? Because it's actually a frame. You can do, that's how movies have been, or let me say, initially that was how movie was being created. And even till now, that's what happens because everything is a frame that is being combined to become a movie or a video, right? So each of these is a picture, a picture, a picture. And the movement we can see here, when I move, when I press this, you can see it moving, right? It's just different. You can see this particular pattern here, this particular image here is this second one. Let me zoom in so you can see it's the second one you can see here, this one. Now, if it moves again, you can see the slow aspect, you can see the legs moving. But it feels like it's one image, but it's not actually just one image. And you can see that it's pixelated at that point. But because of this rendering here on particular uh, this particular website, right, where I'm rendering this, or I copy this to, this actually has removed the pixelation. So, but you can see it's pixelated here, the same image, but here it looks a bit smoother because processing, everything is processing. So yes, what I'm trying to say is, back to the video and back to the animation, is we are trying to implement something similar. It's not too different from what we have before, extremely similar. So that aside, let's go back to this and try to complete this. So that means we want to now, okay, let me close this. So let's create a new file here and call it what? Sprite animation. A new ROS file attached to module sprite animation. Okay, let me just leave. It's going to add the RS itself. So sprite animation, we are not adding this. Basically what we need is what? We need the, okay, we're not going to add the main file. Why? Because we just want to copy what is here. So we don't need the main file by ourselves. We just want to copy what is inside of this place. It's a shame this doesn't have like the copy button, but yeah, it works. So I think it's something we can also add on if I think I can add that to the GitHub. Let's see. Okay, I don't want to go back there. Okay, yeah, let's do that. Let's go for sprites animation or RS and see if we can add that. Create a pull request, but I can't because I've not even forked the repo yet, so it's quite impossible. All right, so that aside, let's just talk about something else. What was I talking about? Yes, the sprite animation. That's what we're looking at. So looking at the sprite animation here, let's see. How is it being rendered here? Oh, so I'm looking at the wrong thing. The sprite animation is already there. Oh, shish. All right, so we can basically just copy from here too, right? It does the same thing, but then we've copied it already. We can paste it here, then we'll go through the code itself and we'll see what is happening. So what we want to implement here is just similar to what we did yesterday and the day before. It is, we look through the example and understand how it works, then we can tweak it and modify it, and we can combine all the things we've learned day 1, day 2, day 3, and also implement it within this third day that we are trying to work with. So yesterday we did a lot on transformations, rotations, meshes, and lighting and colors. So we did a lot on those things yesterday. So we can actually bring some of those things. We can bring some of the mesh shapes back into this place because this is a 2D render, not a 3D. You can still working with 2D. So the sprite animation is also still our 2D implementation. So just putting that out there. Right. So now let's go back to the code and let's see what happens here. Let's try to understand it. First of all, I'm going to run this. Then, okay, no, I won't run this because it's going to compile the previous one because I've not added it to the main file. So it's still going to render the previous one we did yesterday, which is the Bloom 2D. We don't want that happening currently. So I'm just going to leave it for now. And then I'm going to render another one and call it Sprite animation. But now I can't do this because it's not public here. So I need to mark this as public. And then automatically this get accessed. So I can do this and I can rerun this. And automatically, if I do this now, I should get a window that pops up. So automatically the previous window should be, what am I doing? Oh, yeah, it's rendering the first one. All right, so I need to do this. I need to go back here and I need to remove this. What am I doing? Okay, so yeah, I need to do this. And rendering this should give me that new window, which is the sprite, basically. Okay, yes, big mistake here. Reason is because the path is not found. We need it in game assets, textures, but we don't have all of those. We're going to just change the path. Now we can see that it does similar things. We can see the text and we understand how text is applied. We just need to now render the sprite. Now you can see that because the sprite will not be rendered. Yeah, it will be rendered on the app. We can make it render back to the main and changing the default of the sprite. Now we understand why this error is happening. It's literally very clear. So what we need to do is change this. We do not want to disturb ourselves with all of those things. We just have game idle run.png. Very basic, but the name is still wrong because look at the name for our asset here. It is literally game underscore idle underscore run. I prefer to use a consistent pattern, so I'm going to call it game underscore idle underscore run. Consistent naming underscore doesn't really make any difference. So I'm going to do that for this. And then if I rerun this, we should have our sprite image loaded, or two of them. Our images should be loaded now perfectly well. There are no errors here, as you can see. Immediately we run this, we notice the first thing that happened here. The first thing that happened is it automatically animated this, right? But this requires you to use your key to animate this. And you can see it keeps moving. But remember, I said it's the first image. Remember this expression that I gave here, or this analogy that I gave here, that this is just a series of still frames, right? Series of still frames. It's just a series of still frames, still frame here, still frame everywhere. So it's just a series of see, and you can look at the frame. You can do is you can break this, break this, break this. So when we move, we are translating, we are transitioning from this to this to this to this to this to this to simulate the running effect. That's basically what is happening, right? I wish I could cut this into an image and try to run them individually. I think I have an application that does that joins frames, but I don't want to run that now because it will take us away from what we are trying to do. But then probably if anyone wants to see me do that, I can actually do it. Just drop a comment and I'll run that just few minutes, run it, show you how it works. It's actually not a Rust application. It's like a web app that I built that does that, combines frames. So I can use that to show you what I mean, and then we can move ahead. But then that is beyond demand. If you want to just drop a comment and I'll do that. Now back to what we are talking about. So this is the sprite, right? Now let's try observing this code. Let's understand what is happening. Let's see how we can give our own touch to this implementation. Now remember, this is just how many lines of code? 141. It's quite small compared to what we did yesterday. Is very small. We did almost 200 lines of code yesterday. That's 251 lines of code for someone that doesn't even know how to write. That doesn't have like a very expert opinion in writing games or building games with Rust or even writing Rust at all. I can say that if you can do this, then you're pretty good enough to get started, like literally, and that makes a lot more sense. So what we can do next is we can convert this, right? Some of these things we've done here or we did yesterday, and add some of the features into the sprite animation, which we are going to work with today. But yeah, let's take it one step at a time. So the first thing we're going to do is, like we did yesterday, we understand what we need, right? The first thing we need is we need the Bevy imports, which we have here. But remember, just look at this. We understand that there's this other import here, which is the standard time duration. So that means we are simply using duration elsewhere. Let's look for all the places where we use duration here. So you can see we use duration for calculating something. Now, the reason why we use duration here is because when we talk about animation, remember I said this is moving, right? So that means it needs to keep moving. It needs to move from one. Let's say this is 0, this is 1, this is 2, this is 3, 4, 5, 6. It means it moves from frame 0. Let's say this is 0, right? I'm taking it as computer will interpret it. So from frame 0 to frame 6. because there are actually 7 images here. So frame 0 to frame 1 to frame 2, 3, 4, 5, 6. And it needs to transition that within a certain period of time. So we need duration for that to happen. We need duration to be able to understand the time it moves between one frame to the other frame. So we need to write all of this explicitly. Now, that's the beauty of game development. You need to understand how things work, and that's one of the things why the reasons why you need a low level language to write all of this, because you are writing a lot of you are implementing a lot of things, subtle things that you might not do in a high level language. Of course, if you are still writing a game in Python, for instance, you will do all of this, but there's a lot of abstraction over those things that makes it quite, let me not say quite easy, but to an extent a bit more simplified, if you understand what I mean. If you've written a game in Python before. But yeah, but not to dwell more on this, let's start from understanding the code. The first thing we have here is we have our standard time duration, right, which we imported. And if you want to understand more what duration is about, you can see it is used to represent a span of time. So, which what I explained, typically used for system timeout. Now, each duration is composed of a whole number of seconds and a fractional part represented in nanosecond. So you can see examples of how to use duration here. What you just need to do is standard time duration. 5 seconds is duration new 5. That means you are creating a 5 second duration by just declaring this. And you can create 5 seconds and 5 nanoseconds also. That means the first part of this, the first parameter to the new, to the initializer or the constructor for duration is the second. The second argument is the nanosecond. So if you want to do that, you can just declare 5 seconds as 5. 5 seconds and 5 nanoseconds is you adding 5 seconds, adding it to 5 nanoseconds. So that's how you can create time, right? Using Rust. You see how simple it is. Like it's basically just like addition. And for most of us coming from other languages, maybe JavaScript, Python, you can see how easy this is to implement or to create. I hope this makes a lot more sense to someone. So this is exactly what we are trying to do. And yeah, I believe this works for someone, right? Now let's move on from here. So the next thing is we go to our main function. We know our main function is the entry point to our application. So whatever you want to run on start of the application or after compilation on execution of your application, you want to declare it in your main because it's the entry point. That is what the Rust compiler will look for once it is done with all the low-level things and all the compilation processes that needs to be done. And then it precompiles the app, compiles it, bundles it, and when it has an executable, right, or a binary, it looks for that particular thing to execute. Now, in this case, our main file. So once that main file is out of the way, the next thing we need to do is we understand this, we create our app instance, which is initialized, and then we begin to add all the things we need for Bevy to execute using the ECS paradigm that we talked about, the ECS pattern. We talk about adding plugins. We understand we need to add the default plugins. But in this case, we are not just adding default plugins. We are setting the image plugin first of all. Now, what is the essence of this? If you look at the comments here, it say prevent blurry sprite. Prevent blurry sprite. That means on load of your default plugins, you are setting the image plugin to be the default nearest. Don't let us worry about this for now. Like you can understand what it does. It creates image settings with nearest sampling by default. There's something called sampling in image processing. I really don't want to go into this, but there's something called sampling in image processing, whereby it's more like okay, let me give an analogy I was explaining. Remember when I was talking about you joining these frames together and piecing it together? Now there's something called sampling also, whereby you are taking the sample of each frame. That's just literally what it means before you actually convert them into a smooth image. Do you understand right now? So it's something that happens in all these image processor, all these image processing applications we use, like Photoshops and all these complex images, Photoshop Affinity. They have a lot of these image processing implementations already applied very, very well. So one of them is this nearest. If you've worked with all of those softwares before, you see something like nearest sampling. There's another one called bilinear sampling. I think, if I'm not mistaken, right now there's a lot of them. You have options. Even if you work with things like with Illustrator kind of application. Okay, maybe like you work with Illustrator or you work with GIMP, or you work with even CorelDRAW. All of these things have the same thing. I'm just mentioning all the image processing application, all these graphic application now. Yeah, all of them literally does the same thing. No matter the app, no matter the app, they have this image processing ability that they implement, and that's why you can do a lot of all these cool things, because all that is happening there is just you are picking one thing, you are joining this one, that one, you are smoothing them out, basically. So that is what we are trying to implement with this default nearest as well. But like I said, we are not going deep into processing today. So let's proceed. So the next thing is we have the ad systems. Now, ad systems basically takes startup, right? Like we always say, startup is our scheduler. So we were trying to say that on startup, remember, these are like our pattern. We have a startup, we have an update, and then we have like maybe post update or more updates. It just depends on what you want to do. But we understand that startup runs once per frame, once, just once, not per frame now. Startup runs once for the execution of that particular application. So whatever you want to execute or load into the app at the beginning of the app, right, goes into startup. We've said this. I'm just trying to explain for those that might not have followed for previous videos. I really wish you check that out, check those videos out. So link to them will be on any of these videos as I'm talking about it. You will see a pop-up somewhere. You can click it. Maybe whenever you're watching the or watching this, you can click it and then you can activate it and make use of the knowledge from the videos. So yes, the startup does that. Then we have the setup. The setup is the function that runs on startup. The update also is another schedule. It's another scheduler. Let me call it a scheduler that runs once per frame. So it simply means that on every frame render, right, this update function will be called. So that's where you want to execute animations, right? Because once, if it's be run on every frame, then you want the animations to run on every frame. You don't want it to run once and stop, like in this case. And you don't want it to run update once per frame and stop, or you don't want it to even be on a timer. You want it to update once per frame because that already update already does that scheduling job for you. So update will schedule whatever is in this function to run on every frame render, right? That makes a lot more sense. So that's what is happening here. So on update of the frame or of the any frame of the application, it executes the animation. The same thing happens also when you have this. You update this and then you also trigger this animation to run, and you also trigger this animation to run. So we have this trigger animation, we have the right sprites. Okay, let me take this simply. Let's look at this step by step. We already understand the startup, the update, then we have the update too. And then remember, when we have updates and you want to execute many um functions at the same time, you just put them into a tuple. We call this a tuple. For those coming from Python side, you understand what a tuple is. If you don't understand, the tuple is just is a form of an array, right? But that is immutable. For those of you that don't know what a tuple is, and if you are not familiar with tuple, maybe you're coming from a JavaScript side or other languages that have nothing to do with tuples. Tuple is just a data type that is like an array but immutable. That's basically what it is. So yeah, so you want to put that into this tuple, and basically what this means is when you press you want to add functions here that runs also on update. So you might ask the question, why don't we have it inside of this update? Well, we can also, we can, but the reason why this is just to like make it easy to understand that okay, this should execute first, then this should execute also. But at the end of the day, both functions will execute on every frame render. It's just a way of writing your code. You have every right to write it the way you want. It's just preference. So let's move on from that. Next thing we want to do is we want to now look at all of these functions: the setup, execute animations, and the trigger animations. Now, the trigger animations is, we understand now, is a function, right? Because like I said, whatever function is inside there is what we want to implement. So the trigger animation is definitely a function that update will execute on every frame render. So what should happen on this? But first of all, before we work with the trigger animation, let's work with the execute animation that runs, right? Let's look at setup first of all. In fact, let's start with setup. So we are going to take it one after the other. Let's start with setup. Setup. You already understand what setup is. Is what runs, and that's where you have all the spawns, right? Things like you are loading the camera into view, you are loading the camera instance, maybe the camera 2D or camera 3D. You are loading other things like the text, like the node, the text or the images. Everything should happen inside setup because that is where this happens. That's the startup. Remember, everything happens here. So that's simply the same thing that should happen as well. So we have that in this space, and that should make a lot more sense, right? Does this make sense? So yes, let's go to the setup now and try to understand what is there. It's similar to what we did before, what we did yesterday, or what we've done previously. And the essence of this is we have setup where we have initialized our commands. Commands are what we use to create spawns. Basically, they are, for our use case, that's what we've been using since we started this. So commands are what we use to spawn the camera type, which is the camera 2D in this case, because we are still working with 2D cameras, 2D viewports, 2D worlds. So we are still working with that. So we want to spawn our camera, right, at the start of the game. We want to also spawn assets, right, because we need the sprite. So we want to do all of those things in setup. We are spawning the asset, we are spawning the text, we are spawning the camera, we are spawning any other thing, maybe a light source that we want to use within the app itself. We are spawning that as we're into view. So those are things we want to do, and we can actually make that work. Simple. So next thing we want to do is we want to create a minimal UI explaining how to interact with the example. This is where you spawn your text into view. You create a node that defines the position of the text. We already understand most of this. So the first thing we do is we create the text, which is the text you see here, which is this text you see here, left arrow, right arrow. As you can see from here, you see left arrow here, animate left, right, then you break, add the break line, then it does this. So you respect all these break lines too. You can just write it as a text there, just like a normal Rust test, and then it works. So you have the node that explains or that configures the text, right, on what should be displayed. So that's the next thing we have. So after we do that, we also need to load our textures. Now, two things we've done. We've actually spawned our camera. We spawned the text that's going to be displayed. Now we need to also spawn the Gabe itself. That's this guy that we are trying to work with. So we need to spawn Gabe. So let's call this Gabe. I'm going to call this Gabe for the rest of this animation sequence or animation example or animation tutorial. So this is Gabe. We are going to spawn Gabe. We need to also load Gabe. So we need to load Gabe as a from the asset, right? So all I did, in case you are trying to execute the same thing, is I created an asset folder directly on the root folder of my application, not into the source folder, but in be after on directly in the root folder. And then I created Gabe. You can name it anything you want. I added Gabe image sprite images into there, and then I loaded it just like that by just adding the path. Right? You can see there's no external path because it's just directly accessed within the asset folder, and that's all. So all I did was to use the assets server, which we already created as a resource. Remember, we talked about resources the first day. We created that as a resource, and then with the resource, we created an asset server. An asset server in this case is imported directly from Bevy. We don't need to like do anything to use that. It's available for us. So we are just using the asset server that exists, and then we are creating the texture atlas layout also. Now, the reason why we are doing this, we will see very soon. But just know that this is also a form of asset. But texture, if you are familiar with textures or familiar with any image stuff, you know that texture is just something you put on images that makes it change the way it looks, basically. So in this case, too, we have a texture layout. Just look at the texture layout. You can ignore the atlas for now, but is still similar, right? That's what we want to do. But in this case, we after we define what our asset is, we load the asset and pass it into a variable so we can make use of it somewhere else in multiple places. And then the next thing we want to do is we want to use a texture atlas layout, right? Now, what does this do? Basically, let's look at this now. I said we should not bother about it, but now we want to. The first thing we want to understand is what is a texture atlas layout. It is basically used to map, it stores a map, right? And the map is a key value pair. So a map in Rust is a key value pair. Look at it like a dictionary in Python and like an object in JavaScript, right? We have dictionary in Python that stores key value pairs. We have objects in JavaScript or TypeScript that stores key value pairs also. Now, a map in Rust does the same thing. So I don't even know I've spoken about maps since we started, and I said this is going to be beginner friendly for Rust, so you can learn Rust and game development at the same time. So in this case, a map is basically an object type. You can call it an object, right? In JavaScript, if you understand that well, or you're coming from the Python side or any other language, we have dictionaries in other languages and we have maps too. So whenever you see map in any other language that you are used to, right, it's still the same thing here. So that's why we are defining this. So an atlas layout, a texture atlas layout stores a map that is used to look up the position of a texture, right? I remember our texture in this case is what? Is Gabe. Remember I said I'm going to be referring to Gabe, our image, that's this image here, as Gabe, all through this animation, say, and sprite animation tutorial explanation. So what we are doing here is we are loading Gabe as a map, right? And we are storing Gabe, right? You know, Gabe is a position, is a texture right now, and Gabe is going to have positions because we are trying to render him on in our application. So what Texture Atlas does is to store the map of that texture of Gabe himself, right? So we can use that for specific search for specific reasons. We can use that for whatever we want to do, like a lot of things we want to do here. So what do I mean? So let me try explaining in another form. So let's say you have frames, 7 different frames or 7 different pictures. You want to combine them to do something. Now, you know, you first need to store the 7 pictures somewhere. Right? Basically, what Texture Atlas Layout does is to store that frame or those pictures for you, right? So you can use to look up the position of where they are. So in this case, depending on the picture you want to load second or first or third or fifth. Now, what the texture atlas layout will do is to take all of those images for you, store them, so you can actually get the position of any of those images, and then you can make use of it wherever you want to do, or you can swap their position. So because swapping the, remember, once you start rendering them, you can't swap the position anymore, but you can swap the position to how they will get displayed. For instance, if you have like all these screensavers on your phone or photo screensavers, whereby it just picks your photos. There are times you pick randomly, there are times you pick sequentially and load them for you. That's exactly what the texture atlas layout is doing. So it will store a map of all the textures of your texture. Let's in this case, Gabe, right? It will store a map of that of Gabe so that I can look up the position of any of the frames of Gabe. Now let's go back to what Atlas is. So texture atlas layout, yes, stores a map used to look up the position of a texture in the texture atlas. This can be used to either use and look up a specific section of a texture or animate frame by frame as a sprite sheet. You understand from the explanation I just gave. So optionally, you can store a mapping from subtexture handles to the related area index. So let's not dive into that. But you understand from the analogy I gave of having different pictures and then you're trying to animate them. It simply means you have the pictures and then you arrange them in sequences or and how to display them. And then in this case, you give it a software, or if you are using an hardware, you render them and then to render each one sequentially, right? In this case, the atlas layout, the texture atlas layout is what you add your texture to that stores the position of all the frames. So now let's proceed. So the sprite has seven, the sprite sheet has seven sprites. Remember what we said? It has seven. 1, 2, 3, 4, 5, 6, and 7, which I was saying the other time is from 0. Let's say this from 0, from 1, from 2, from 3, from 4, from 5, from 6. But basically, there are 7 sprites here in this sprite sheet. So what we are trying to make use of here also is we have, okay, look at this here. This sprite sheet has 7 sprites arranged in a row, and they are all 24 by 24 pixels, right? So what we can do in this case, we can now break it down. How do we do that? We are using the texture atlas layout to store all the frames, the sprites now in this case, by their frames, and then we are going to store so we can keep track of their positions. Now, what does that mean? It means we initialize the texture atlas layout, and we create, if we use a from grid, right, as a function on Atlas layout. Remember, Atlas layout is what is a struct, right? So we use the from grid as a function to get to store rather the value of all we want to use. So to generate a grid based on, like we said, the storing the positions of the sprite. So this is from grid is going to store the position of all of our texture. So in this case, we are simply generating a grid where each of the title size. Okay, let me just go through this and see the documentation. Generate a texture atlas as a grid where each tile size by tile size is one of the sections of the atlas. Grid cells are separated by some padding so that, right, you understand, there's, see this padding where I added these arrows, yes, so that you don't see breaking animations as if it's warping or something. That's why we need that. So the from grid is going to do that. It's going to generate a grid. It's going to generate texture atlas layout as a grid where each tile size by tile size grid size cell is one of the section in the atlas. Grid cells are separated by some padding, and the grid starts at offset pixels from the top left corner. Resulting layout is indexed from left to right, top to bottom. So we are going to see everything we are talking about here. So the first thing is from grid, like you said, stores it in a grid form, right? We understand what a grid is. A grid is basically you having something like this, and you have arrows. Let me use arrows to separate them. So in a grid, you have something like this. You can change this color from, let me use red, so it's clear enough to see. So it duplicates this, duplicates this. So let's say it's a 4 by 3 grid. So I'm going to duplicate this and create another grid. So this is, let's say this is a 4 by 3 grid sample, right? And yeah, so let's say this is a 4 by 3 grid sample one. This is a grid, basically. Ignore the arrows. You get what I mean? But this is a grid, basically. So this is a grid. Let's say this is a grid. Now it's looking more like, okay, so it's looking like a grid 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is like a grid. So let's say this is a 3 by 4 grid. 3 in the sense that, okay, 4 by 3. It's a 3 by 4. The 4 by 3 grid. Okay, yeah, I think it's 4 by 3 grid because you take the row first and the column next. So, oh yeah, it's a 3 by 4 grid. 1, 2, 1, 2, 3, 1, 2, 3, 4. So it's a 3 by 4 grid. That's correct. So it's a 3 by 4 grid basically. And this is just a grid, right? So it's going back to what we have. So we are taking this sprite, which has 7, and we are storing it in a grid. So basically, we are creating a splat of. So first thing we need to do is, because we want to create as a grid, right? We need to create a two-dimensional vector. The reason for a two-dimensional vector is because, remember, it's a 2D image we are working with. So we need to store each of them inside a vector. A vector in this case is just something like having an x and y axis also, which is more like you are storing it in this form. So look at each of this cell as creating a vector. Now, that is not exactly perfect, but it works for this use case. Look at this cell as creating a vector. And what you are trying to do with that is, you are basically saying that you are creating a u vector, a two-dimensional vector in this case, which is you use uvec2 to create that, and then use the splat. Now, you may be wondering, how do I understand all of this? The truth is, you don't need to remember most of these things. If you need it, you find it, because software engineering is about finding and making use of it. You look for what you want, you make use of it. If it works for you, if it doesn't, you discard it. It's all about swapping in things and swapping out things. That's basically how it works. That's how everything in software engineering works. So don't feel like it's too much and you can't understand what it does. So that's the first thing. So the next thing is, we have the splat. In this case, that's uvec2 splat. And in this case, what this means is, you have the. So this splat, now let me explain what this splat does. Now, it's basically okay. So first of all, we've talked about the vector, the two-dimensional vector, which is uvec2, right? So we're using this splat to create the vector, to create the elements, not the vectors now, to create each of this 24 by 24 pixels sprite in these vectors. Remember that I said that look at these cells as that. Yes. So we are creating something like that. So we are creating each of them. So we are creating the position of this. So in this case now, V in this case is like you are creating all the elements to like a vector. So you are creating them as a vector. But in this case, you are creating a two-dimensional vector, and you are putting each of them as a vector. This means this is 24. In this case, 24 pixels, right, as a number. And then, because we are creating that, remember that from grid here, let's look at what it takes first of all. From grid takes a vector size, which is the tile size. It takes in a column, it takes in rows, it takes in padding, and takes in offset. The reason why we need the tile size is so that we can know the size to allocate for our tile, so it will not be too small or too big. Depends, it may be bigger, but it should not be smaller. If not, you have warping animations. So that's the reason why we need that. So look at this as the tile size. Like I said, look at each of this is a cell, right? So this can pass as your vector. So what you want to do is, you need to define your vectors. So what you want to do in this case is define the size of your vector from, that's what we are passing to from grid. So for us to define the size of it, our tile size, it needs to be a type of what? uvec2. So if you want to use this, all you need to do is to understand the signature of the from grid function. You already know that is a uvec2 type of argument you have to pass to it. So what you need to do is use uvec2 to create the dimension you want, or the size rather, that you want to pass to from grid, so which is 24. So once you specify it as 24, the next thing we want to pass is what? The columns. How many columns do you want? 7. The reason why we want 7 is because look at this: 1, 2, 3, 4, 5, 6, 7. If you look at the way it is now, remember, it looks like this grid that we define here. This is rows. Remember, this is one row. How many columns? 1, 2, 3, 4, 5, 6, 7. In this case, we have how many rows? 1, 2, 3, 4 rows, but we have 3 columns. 1, 2, 3. Right? So that's what we are doing here. So how many columns do we have? We have 7. 1, 2, 3, 4, 5, 6, 7. How many rows? Just one row. So that's what we defined here. You can see from grid takes this as parameters: tile size, column, rows, padding, and offset. Remember, we also say we need to add padding to it, right? So that we don't get mushy. The frames don't intertwine into each other when they are rendered. So in this case, we are not adding any padding currently. You can see padding is none, and then the offset is also none. Or we cannot padding to it because padding is also a number type. Padding takes in an option of u vector 2, right? It's also u vector 2 type. So that means u vector 2 means we need to create it similar to the way we created this if we want to add padding. Don't worry, we can always tweak it eventually. Let's understand what's happening first. So the next thing we do here is we define the texture atlas layout. And how do we do that? We say texture atlas layout. We add the layout itself, which is this that we've defined, to the texture atlas layout. And where did we declare the texture atlas layout? We are initializing it here, right? And we are adding this layout. Where's this layout coming from? Remember this when we define this as a resource with asset and this. Exactly. So we are now adding our layout, which we define here, which is just the grid that we created, we are adding it into the texture layout now. So that means we've successfully created our layout of all the sprite frames. Does that make sense? I really hope this makes sense. I'm not getting any feedback from you guys yet, but I believe if it does, please say something. Let me know if it makes sense. And if it doesn't, you can also comment whenever you're watching this. Even if you're not watching it currently, you can always drop a comment and then I can always go through it, give you responses as to whatever issues you may have regarding this up to this point. But I hope this is clear enough, right? I hope this is like extremely clear enough based on what I'm doing. So that's the first thing. So the next thing here is successfully now we've done two things or three things. We've spun our camera, we've created our text, we've created our texture, we've loaded our texture, which is our sprite image, which is Gabe, and then we've created the layout, the asset layout for Gabe, right? And that means all the sprites, all the columns for the sprite of Gabe have been created, right? Just think of it that way. So all of them have been created and loaded into memory. So the next thing we need to do is we need to create the animation configuration. The animation configuration, you understand what it does, but at least the name should give you an idea of what it does. We are creating the configuration of and the animation should run, right? That's basically what we need to create now. So because we are trying to render something that does this, that enables you to run the app like this or run the animation like this. You can see one is running faster than the other. You can see this right one is faster than the left one, right? Okay, so that's basically the first thing we have. So let's go back to this. So we have this. Let's create an animation configuration. Now the first left-hand sprite, right, runs at 10 frames per second. That's why you can see, like I said, you can see it runs slower. You can see it runs slower. It's not as fast as the one on the right. Look at the execution speed. You can see it's very slow compared to each other. Now that's the first thing. So that means that for us to define the animation, how it runs in terms of speed, what are we trying to do here? We are trying to make sure it runs at a lower frame rate than the one that moves faster. Now you understand where frame rates come in now. If you are working with things like this, that is what we are talking about. So this is where frame rates come in. So if you are playing games that kind of like lags most times, you notice that you say, oh, if you use a higher frame rate, a device with higher frame rate, it will be faster and stuff like that. Or they'll tell you that, oh, can you increase the frame rate maybe from 30 FPS to 60 FPS on the settings, and everything becomes smoother. This is basically why. Why? Because you are configuring that game to run faster. Now, from the basic of levels of explanations, this is basically what is happening. From here to here, you can see the speed difference. Exactly. So that's what we are talking about here. So the first thing we want to do is create an animation configuration. And what do we use? We use an animation configuration that exists from Bevy. Bevy already creates it for us without we needed to do anything. So what does this mean? Create an animation configuration and initialize it. Initialize with what? The first frame, the last frame, and then the FPS to be what? 10. Does that make sense? I'm sure that does. So we already understand what this is. So we can see that it is never stopping. So if you realize this, we are starting from the first frame. Remember the analogy I said of 0 to 6. Frame 0, frame 1, frame 2, frame 3, frame 4, frame 5, frame 6. So what we are simply saying is what? Start from what? Frame 1. That's why you can see from this execution that no matter what, it is not, there's no idleness, there's no standing on this animation. Look at it now. You can see this first animation stands. Then this one moves. You can realize that this is the initial. Look at it well. You can see the initial position is what? This one. So just to give you a bit of context, this is, let's see, this is, let me write this 0. Let me put this here. This is 0. This is 1. This is 2. This is 3. This is 4. What am I doing? No, okay, still perfect. This is 5. And this, no. This is 5. And this is 6. So in this case, let me write this. This is 0. This is 1. This is 2, 3, 4. No. Okay. 5. And this is 6. Now, you understand this is just the frame itself, right? These are just their frames themselves. Now you can see. So this is, we are not using frame 1 from 0. We are starting from frame 1 and ending at frame 6. And that is what is exactly happening. Let me use the slow one. You can see it moves from frame 1 to 6. The 6 that ends in is the running frame also, but it seems to be running a bit more faster. Let's observe it. If there's a way I can slow this down a bit more, just to show you guys. Let me run it at frame rate of 2, so you can understand what is happening here. Now you can see it's very slowly. Now if you observe it slowly, now I'm going to run it again. You can see what happens. It started from this initial running to moving to, notice the second one is this, the third one is this. Just observe it again. Does that make sense? So at the end of the day, you see that the last animation before going back to the first one is the one where the legs is stretched like that. So there are two stretched ones. This one is stretching like this. The other one, observe the hand of the last one and the hand where it's stretching the first time. So let's check it again. Now you can see the difference. So now this is very, very low. So I've reduced the frame rate to just 2 FPS per second. So you can see how slow it is to execute that. Now compare the difference in speed between this and this. You can see this one has finished executing and this one is still maintaining the first execution. So I can run that 5 times before the previous one executes completely. So that's the difference in frame rates, right? I hope that makes sense now. So that's what exactly is happening here. So we're starting from the first frame to the last frame and executing it at 2 frames per second for our use case. Initially it was 10, and you see how slow it was. Now that I made it 2, it's extremely slower than when it was 20. So that's what we are trying to explain or implement here. So the next thing to look at is what we have to create the first left-hand frame, which is the one that is slow that I just showed you guys now. So what we are trying to do is we try to create a sprite. Remember yesterday when we tried to create a sprite, we said that we need to use the sprite keyword, the sprite struct, to define your sprite. So that means you need to define the image that you want to load as a sprite. So that means our texture. Remember we created the texture here, and then we need to clone it as our image. Second thing we need to do is we need to initialize the texture atlas. Remember we said the texture atlas is just the definition of the layout created for that, or of the grid of the layout basically created for our texture. Now if you go to the bloom yesterday, we didn't have that sprite, but we also created the sprite. Where is it? Did I? Yeah, this is the sprite. Remember what we did? We added the image, we loaded the image here, we defined the color for that particular image. So in this case, we are adding something bright just to see the effect. Then we define the custom size for it, and then we loaded the default. But in this case, because we are dealing with a sprite and then want to make that transformation or the animation, what we need to do is to define the texture at last and then the default other default configurations. You can also define the custom sizes if you want, but then that's also just defeats the purpose of the default atlas in this case. So now also the texture atlas has its own configuration. Now, why? Because we need to also define it as a texture atlas, because when we are defining this sprite as a struct, it has an image field, it has a texture atlas field that is a type of texture atlas. So that means because it's a type of texture atlas, we also need to create a layout for it, or we need to define the layout for it, which we have created already, and then we need to define the index, which we have already created, or partially. So the first thing we do is just like we clone the texture, right? That means we are not giving it access to texture. We're only passing it by what? Borrowing. So we are borrowing this sprite, the texture to use. We are not giving it ownership over texture. That's what we are simply doing here. That's the reason for the clone. So if you have ever come across the borrowing or the borrower ownership um, analogy in Rust, this is basically what we are talking about. We have the borrowership and the ownership analogy. This is what we are talking about, the texture and the clone, right? The clone rather. So we are talking about the clone. Clone means you are cloning the original copy or the original entity, right? And we are borrowing it. So in this case, we are borrowing the texture so that we can use it elsewhere, because if you give it to this place, that means we are giving image ownership of texture. That means it cannot be used elsewhere. If not, it's going to throw an error. So also doing the same thing for texture atlas, we are cloning it, not giving it ownership over the texture atlas. So in this case, we are doing those two things. Then we are defining the index for the atlas. And what's the index? Remember, we already defined that our animation configurations will start from the first frame and then the not the zeroth frame now. or let me say the second frame, that's frame 1, not frame 0, like we define here. Start from frame 1 and end at frame 6. Now, that means you should start from frame 1, that based on the configuration. So in this place, we are using the configuration as our index and saying that animation config 1, which is this first configuration, dot first sprite index. Does that make sense? So the first sprite index simply means the first one that will be loaded, which is the first sprite, based on what we defined here, which is 1. If we define 0, it's going to load 0 as the first one. I hope this makes sense. All right, so now let's move on. The next thing to do is to define a transformation on that particular sprite now. So what's our transformation going to look like? A transformation means we are creating a from scale, right? For that particular sprite now, we are creating a from scale, just like we created yesterday from translation. Or is it from translation? Let me be sure. Yeah, from translation. We created it from translation yesterday. So today we are creating a from scale. Scaling is just different. Translation means movement. Scaling means you are increasing the size, right? You are scaling it up or scaling down, depends. So in this case, you are creating a splat. Remember, we created a splat when we wanted to initialize the u vector 2. A splat in this case is just a way of creating a particular vector. So in this place now, we are creating this vector of 6. In this case, we are creating 6, a vector of, we are creating 6 vectors, right? Using, we are not using uvic2, we are using vec3. The reason is because, like I said, if you look at from scale, you can see from scale takes in a vector, a data type of vec3. So you already know what to use. So if you are curious, when do I know what to use? Once you know the signature type of your function you are trying to implement, you can actually decide to use it. So in this case, I can't use a vec2 because it's going to fail. I have to use a vec3 here, because that's what the function expects. Remember, I didn't write the function. Bevy already wrote the function. I'm only making use of the function for my use case. Does that make sense?
It's 17 hours.
So that's basically what we are doing here. Sorry guys, I had to take water. My throat was running a bit dry. All right, so that's basically what we are working with. And going forward, next thing is we define the vector type, and then we add a translation to it. Now, what does the translation mean? We are defining the translation for this particular vector that we created 6 vectors for, right? We are defining a bit translation for it. And now run the transform with a new translation. That's this particular transform that you scaled. You are running a translation from it. And the translation you are running from it is about to move minus 70, right? You are still going to see all of this in action, just like we did yesterday for the bloom, and see the movement and the differences. The reason why I'm taking time on this is because once you understand this concept of animations, we can actually use this for the sprite before we move into the 3D handling and modeling and other things, which we are still going to talk about. So makes sense, right? So yes, I believe this makes a lot more sense to you guys. So now they are defining the translation. In fact, just to be clear, we already understand. Just try looking at where this is. Look at the difference between the two of them. Look at the position and all. Now let's reduce this from 70 to 20. And let's do something here. So I'm going to rerun this. I'm going to compile this. So once I run this, it's going to recompile itself and it's going to display. Now you can see the space between both of them is very low. Now because I've added it together. Now the essence of this is just to give them space between each other. That's why this transformation exists. I'm just trying to point it out so you can see why we are adding different things to our program. Now, a program is just a combination of different logic, blocks of logic. So say I want to build an house. I know the first thing I need is a foundation. In this case, we've created our foundation, which is what? The app.main. We've created all the pillars for the foundation, which are this, right? And then we now begin to execute each of the pillars. I want this pillar to be 4x4. I want it to be 60 centimeter high or 60 meters high or 60 whatever, this and that. That's exactly what program is all about. The program is, and remember, we are still working with the setup. We've not even gone into the execute animation aspect, but we're almost done with setup. Once you understand the setup, execute animation is basically you making use of everything you have defined in your setup. So your definition for your setup makes it easy for you to add logic to the setup. Remember, this is what we talked about for the previous 2 videos before this one. So that's basically what we are trying to do here. So now let's go further and create something else. So Okay, before we move on from this, let's look at this now. Left sprite. So what is the left sprite here? Do we define left sprite somewhere? Yes, we define this struct of left sprite. That means we define it as a component. Remember, we talk about a component ECS. Remember the ECS, entity component system. Exactly. So we define the left sprite as a component and the right sprite as a component. The reason for this is because so that we can actually add logic to it. So this is the left sprite. This is the right sprite. So we're just giving this so that we can make use of it within the system, so that we can make reference to the sprites that we've created within the system's logic, because we are going to have system as functions that define logic for each of the components, right? That's the essence of the ECS patterns. So that's what we are doing here. So for this spawn, we are spawning this to be a sprite, to have this transformation, and to have the left sprite, and then to have the animation configuration 1. And what is the animation configuration 1? Which is this guy. The configuration for the animation is what we are defining on it. And you can see that we are adding that to a particular spawn. That makes a lot more sense, right? Okay, so we're done with this. So let's go to the second animation. It's basically the same thing as the first animation configuration we had. So we had the first one as 10. I changed it to 2 to make it extremely slow. I changed the position from 20, 70 to 20. I can make it 100 or 120. Okay, let's make it 100. From 70 to 100, so that by the time it is being rendered, it won't be too close to each other. It will be extremely far away from each other. Let's try that and see. So it's going to be far away from each other, or farther away from each other than it was before initially. Now you can see it's farther away from each other. Now, if I want to play with it more, I can make it 400, and it will be extremely far away from each other, as if they are trying to run to meet one another. Right. So that's basically what we are trying to do in this case. So you can see this now. You can see the distance. You can see how far away it is. So that's the essence of the transformation that we added here. Simple? Exactly. So the second thing is, I can just, if I was the one writing this, all I would do is just to duplicate this animation configuration, because it's literally the same thing. All I'm doing is just changing parameters to what I want. In this case, I'm adding 400 here. In this case, I'm adding 70. I can increase it to 100, 170, add right sprite. It's literally the same thing, right? Like nothing different. The only different thing you see here is this default. You have default here as default, which still the same thing. So that's basically the difference, right? So now we can confidently say we are done with our setups. We've loaded everything we need. In this case, if you look at this, what did we need here? We needed to load the camera, right? Because the camera is what you're using to define the perspective and the lighting systems and all, where every other thing builds upon, because that's what gives visibility to the world you are creating. So take this as you are creating a world. We need the camera to see into that world. So that's what we defined. We defined a 2D camera that allows to see the width and the height of the world we are creating, not the breadth. So for us to define something that gives us access to that, we need a 3D camera. But in this case, we created a 2D camera. We created a text, right? So that we can render a text. So we spawn the camera into the app. We spawn the text into the app. We spawn the textures into the app. And then we define the way the textures should be rendered on screen by defining them as, by giving them the translation, the transformations they need, and defining the component for each of those sprites. And that's exactly what we've done. Make sense? Yeah. So now that we've concluded with setup, let's do this next. So let's look at execute animations before we even proceed to what this is. The trigger animation should be simple. That is just definition with your key press. So let's talk about the execute animations. How do they run? Now that we've defined what they should do, we know we've already defined everything. From what we've seen so far, we already understand that the animations we are fine to be executed. So what we need to do is we need to loop through them so that they can run from the first sprite index to the last sprite index. Simply mean we need to loop through them to execute from 0 to 6, or in our case now, because we define it to start from 1, to start from frame 1 to frame 6, not frame 0. So in this case, that's what we want to do. So we need to implement a for loop. I know that for us to define it, anything that has to do with increasing from one level to another, we need a time, because we are working with time in games, and in, yeah, let me say in games, we are working with time. The reason why we work with time and everything else to do with time is because time is the way we can keep track of what changes and what does not change. Just like in the real world, we need a time for everything we do. We need a time to know that, okay, we started this, for instance, we started this day 3 series by 4 p.m. Nigerian time, West African time. And so far we've gone 1 hour 7 minutes into it. Now time is what gives perspective of what we've done so far and what has changed. And we've realized that we've learned certain things in the span of an hour. If there is no concept of time, we don't know what we've done. We can only know that, oh, we did it when, how, okay, we did it at this also time, like this and like this. So it gives meaning to whatever we are changing and not changing. So that's the same concept in this place. You need time for everything you are implementing, basically for change of state. So in this case now, we talk about time, and we are creating time as a resource. This is how we've been creating it since we started, and that's basically how it's going to be for a while. It won't change much. So it's almost always going to be similar syntax going forward for most things you define. So when we do this, we say time, we create time as an instance of as a resource, right? Because time is a resource in this world. Is a resource even in the real world. Yeah. So then we create that, and then we create a query for two things. What we are going to need. So think about it this way. What do you think we are going to need for the animation before we even dive into whether our query here is correct or not? Of course, it's correct, but think about why the person decided to write the code this way in the as the example. What do we need to query to make our animation run successfully? Remember that we've already spawned. So let's say we did not. It doesn't run currently. This is how it is. Let's say we don't have access to all the other part of the code that makes it run, but we spawn the code like this so far, right? We spawn them, but the key press does not work. They don't animate. This is just what we have, and it's fine. Now, what do we need to do to make sure that the frames, this frame, right, they move? Two things we need. We need to animate them, right? And that's exactly what we have here. And so we also need the sprites themselves, or the textures. Let me call it sprite in this case. We need two things. We need the animation and we need the sprite. But first of all, we need the sprite and we need to animate them. So what do we need to query for this animation to be complete? We need to query the sprite and we need to query the animation for the sprite. So that's exactly why these two things are being fetched. So it's just for you to think about what you need to fetch your query. Remember when we did the Bloom yesterday, we realized that we needed two things. We needed, when we were talking about adding them, right, trying to add rotation to it. It was not something we've seen so far. There was no example, direct example for our use case. But we created it, we looked at another example, look at how it was done, and added it to our own logic. And it worked. So what we did was we realized that when we wanted to move the shapes. The only way we could move the shape is to have the shape. We need the shape to move the shape. We need the what else do we need? We needed the shape. We needed the transformation that we wanted to apply on the shape. So in this case, two things we needed. Time is always constant for this. We need time. Always need time. We needed the transformation that we needed to apply to the shape, to the rectangle. In this case, we needed the direction where we are going to rotate them to. And we also needed what? The transformation also. So, but in this case, this was already defined for moving the property, the shape, which was the circle. Yeah, we needed this for the circle, which worked. But we wanted to add rotation. What do we need for rotation? We now thought of it that okay, we needed rectangle and we needed transformation. And that was why we decided to use this. But in our own case yesterday, we didn't need to query it at all because we already have a query of direction and transformation. But in this case, we needed the rectangle and the transform, but not to query it. Of course, we could query it also because we are actually making use of it from rect transform because we are making use of it, we are getting it, and we are passing it. But in this case, there's already a query here that could give us most of the things we needed. But in this case, we are not trying to query the rectangle. We just need something from the rectangle. But aside from this now, that's just aside. All we needed exactly was the execute animations, and then we query this, the animation and the sprite, to be able to track what's happening there. So how did you do that? The first thing we need to do is to implement a loop. Like I say, we are moving from frame 1 to frame 6. So what we needed to do was to implement a loop, an actual loop that makes it work. Does this make sense? I think it does, right? I can't know if you guys understand this, but I believe I'm trying to explain as easy as possible so you guys can follow anytime you are watching this or if you are following at this point in time. So the next thing is we need to do that. We have this loop for this in this, right? And then we need to have a loop that loops from frame 1 to frame 6. So that's basically why we have this for loop here. And then we say for, remember we are working with two things, the animation and the sprite. And currently we already have the sprite defined. So first thing we need to do is to structure the query. The structuring the query in the sense that we have the query here, which is a mute, an animation, config, and a sprite. So we destructure it as config and sprite. So we want to track how long the current sprite has been displayed for. That's the first thing. So how do we do that? We define the config. Config has the property of called frame timer. That's FPS, which we define. Remember, we defined the FPS, and then that means because we already defined the FPS and the first and the last index, that means we can access it by first sprite index, which in this case is going to be what? 1. In the last case, sprite index is going to be 6 because that's what we defined for it. So now in this case, we're using the frame timer, which is an instance of timer, or you type an instance of timer. So we are using that to tick. In this case, tick is just like the tick of a clock. Remember, I told you that everything we do in this in the gaming world is working with time, just like we have in the real world. The way the second tick is an instance of something have passed. And for every moment that passes, something happens. A state changes. You grow older. You become hungry. You become full. Do you understand? A state changes. That's the same thing that happens here. In this case, also a state is changing. You are changing the state from for every second that move, every second that change from when the app was started, like what we have defined here. From the time I defined this, opened this window or created this window till now, certain things have happened. There are many things happening in the background, but because I'm not doing anything to animate this sprite, it feels as nothing is happening. That's the same way it works when you are sleeping. It feels like you are sleeping, but nothing's happening, but things are actually happening around. But because you are just unconscious at that point, it feels nothing's happening, but time is moving. That's the same thing that happens here. So whenever you use the tick, the word tick, means you are moving from one time to another, just like this, the movement of a second. But in this case, we are moving, we are checking the configuration timer, right? We are using an instance of the frame timer and applying the tick to know how long the sprite has been displayed for. Do you understand? That's the first thing. So we're using the timer to know, okay, this configuration, when did it start, or how long has it started, or how long has it taken to start and to end, or how long ago did we render this animation? I think that's the best way to put it. How long ago did we render this animation, or render this sprite rather? So that's what this is. This is actually, let me even change this to make it work. How long ago have we rendered this sprite? So that's basically what it means. So the next thing we need to do is if it has been displayed for the user defined amount of time, that's for the number of FPS. Now remember, now you don't understand what the FPS is meant to do. FPS means the number of time it takes to run. In our case, we defined our FPS for the first app, which is the one by the left, to run in 2 FPS. That means it should run 2 frames per second. In this place, we are simply should run 20 frames per second. What does that mean? It simply means if you expect it to run per second, a second in this case now, it's just like you saying that you want to um these competitions they do that say, okay, who is the fastest in this place? Somebody's going to be the fastest in a race, basically, maybe 60 meters or 40 meters. I know that let's say 60 meters takes 2 minutes to run. That's like just an example. Whoever runs fastest can do it in 1 minute 40 seconds, right? It simply means the person has a faster speed than the other person. It simply means if you want to calculate it, we can say the person is running at 20 frames per second. In this case, the person takes 4 steps per second. Let's assume that's how it is for an 100-meter race. Let's just use an analogy. So let's say four steps per second. The person that takes 4 steps per second is going to be faster than the person that takes 2 steps per second, right? Why? Because the person moves slower per second. So that's exactly what is happening here. In this case, you are moving 20 frames per second. That means you are running faster, you are executing too many things. You are doing multiple things per second than someone that is going to do it 2 times per second, 2 frames per second. Remember, I said everything is rendering as it is like this, even being idle. Something is happening at the background. It keeps rendering the same thing. It's in a loop as it is like this to render the sprite. So as it is currently, it is in a loop that keeps rendering. So for every frame that renders, we are saying that execute this animation twice, and that's why this is very slow. You can see. So it splits the execution of the animation into how long it's going to take to execute in 2 seconds. And it splits this animation into how long it's going to take to execute in a second rather. So it divides Okay, that came out wrong. Let me explain. You divide this animation in how long it's going to run, right, per second, and multiply that instance by 2. So it takes division of how long this is going to also run per second and multiply that by 2. So this is there are 6 frames here that should run, right? So if it's going to run 20 frames per second, that means you should execute this 20 times per second. You should execute this just 2 times per second. So this is obviously going to run much slower because this has more time to take time to run. But if this is going to run 20 times per second, then that means it has to be way faster. Just like you say, oh, I give you a chore to do in 30 minutes, another person to do. So let's say, for instance, I say, okay, you need to go, you need to wash, do all the laundry in the house. You need to do the laundry in the house, and you both have 30 minutes. So I give one person in the house to do the laundry of 4 people, and I give another person a task to wash the dishes, just 5 dishes. The person that has 30 minutes to wash just 5 dishes is going to take his time, right? You could wash one dish for if it's 30 minutes, divide by 7, right? You can take 7 minutes to wash one dish and you still complete before 30 minutes for 4 dishes. The person that has to wash laundry for 4 people, let's say each person has 10 clothes they want to wash, right? So he has to do laundry for 40, he has to do 40 pieces of laundry. Do you understand? So that means if you are dividing that by 30 minutes, so that means the person needs to wash each cloth at least, even though he's going to use a washing machine for the laundry, right? It needs to split each laundry execution by at least 7 minutes to match up to that. So if he decides, okay, I'm going to wash for each person, I'm going to divide by 4. So for each person is going to get 7 minutes for their laundry, both washing, rinsing, and spreading. Do you understand? So the person washing place is going to take slower time. The person washing is going to multitask. That's exactly what is happening here in the frames. So that's why this runs faster. This person is like actually rushing to get everything done because he has the same number of time as this person that has enough time to execute the same thing within the same render time. Remember, both of them have the same time, just like in the world, we have the same time. So that's exactly what is happening here. So now, if the frame has finished, just based on the way we explained it here, right, we determine how long we've rendered the sprite. So if it has finished executing that frame per second, and the atlas, we are going to initialize this with variable, and we have our texture atlas, and basically, yes, we do have our texture atlas, and it's fine, there's no error. So what we are going to do is we are going to take our atlas and get the index and say the index is going to be our last sprite index. That means if it is done, right? Now, that means if it is finished displaying for the user defined amount of time, that's for the number of FPS, and it is the last frame, then we move back to the first frame and stop. Remember what I said the other time, that when I was showing you guys these two, let me show you again to explain. This for the slow one, look at, just observe it. You can see that it goes through all the frames, gets to the last one, and goes back to the first one. This is the first frame, which is frame 1 in this case. Observe the last frame, which is frame 6. If I take it again, you see this. This is frame 6. Do you understand? That's frame 6. I can't pause it, but I will have shown you guys. That is exactly frame 6. So that's the condition we have here, that if it is the last frame, that's what we are saying, is if atlas or index equal to the last frame, that's the last index. Atlas index is what? From texture atlas. Remember what texture atlas do? It stores the position of each of the frames. So we are simply using that atlas to get the position and saying that if the position in the atlas is equal to the last frame index, then go back to the last frame index. So we are setting the index of that particular atlas to the first one and stop. Else, if it is not the last frame, then move on to the next frame. And what does that mean? Start from atlas of 0, because once we define it like this, the current atlas is going to start from the first one we define. But in this case, it's not going to be 0, it's going to be 1. 1, why? Because we define it to be very set up. We define it to be what? 1 from an animation configuration. So that's what we are going to do in this case. Yeah, this is it. So we are going to define, so we are defining that. So in this case, we are saying that move step by 1. So it's going to step by 1. So it go from the first frame to the second frame to the third frame to the fourth frame, fifth frame. When it gets to the sixth frame, this condition becomes true, and then it goes back to the first frame. If for any reason at all we remove this, just watch what happens. Let me rerun this so you can see what happens here. You can see it stops at this point. It stops at frame 6, literally at this frame. Let me zoom this in so you can see. You can see that it stops at this frame, not going back to this. You can see it. So that's exactly what's happening here. Does that make sense? Yeah. So that's exactly what we have here. So it starts from there and stop at first index, at the last index. But in this case, if it is not the last frame, then keep going from one frame to the other and reset the frame timer to start counting all over again. Do you understand what that means now? Exactly. So config.frame timer simply means that after you've done after you increment the frame, let's say you are on frame 1, it goes to frame 2, it goes to frame 3. The moment it goes to frame 2, it resets the frame timer to start counting all over again. Because remember we said that every frame, the frame, this app here renders per second. It renders per second. So once you are done, just like it is frozen here, instead of it to be frozen so that it does not freeze, we reset the time. So the time moves again. Because it's not like the wall clock we have here that keeps counting. Right? So we are simply saying that the config frame timer should be the timer from the animation configuration. Remember, the animation configuration has its own time that we defined. Let's go back to where we defined the configuration. Where is it? Where is it? Where is it? Yeah, this and this animation configuration, we defined it here, which is animation configuration that we used here, defined as a component. And then we implemented it here to do certain things. We implemented the self, which is the initialization for the struct. And then, wait, did I mention this was from, I think I mentioned this was from Bevy, right? Well, typically it was defined here. That's why we have access to the first frame index, last frame index, and this. And then we just define it since we know that it's coming from first, last, and FPS here. Oh, sorry about that. That was a mistake. So it's actually defined here and then it is implemented. And that's why we have our timer from FPS defined. A timer from FPS is just an implementation on animation configuration. So that's basically what we have here. And yes, we have that, and then we have the timer, which results to a timer. So basically, when we loop through that, and yeah, to get the timer here now, just now, if you look at what we've been implementing since, just to give you an idea of how all of these things was created. Now, this is even a good way. Look at this animation configuration. You can see it's just a struct, right? And it's a struct that's implemented. And remember this new that we see everywhere, just like we see on timer.new. Timer is coming from Bevy, not from us. And you can see animation config also has new. New is just like you're initializing a constructor for the struct. Look at it that way. So if you look at the main also app.new, you can see app is just a struct in this case too, like we said, right? So you can see the same new implementation. We basically have it defined here. So you can write your own struct also that way as this, having new and taking in parameters, right? And returns is an instance of self. That's the struct itself. And then you define what happens here. That means you're saying for when you define your application animation configuration, which is the same thing we did. Here's the setup. At this point, we said .new first of all, and what was the next thing we did for the animation configuration? We just passed it to this, and when we wanted to use it within our execute animation, what did we do? We can now access the timer from it. We can access the last sprite index, the first sprite index, because we already defined it here. Now the timer from FPS, which is this function we defined here, look, imagine, see how we access this also. We used the colon to access it also, and passing definition, and which is just an instance of timer.new duration from seconds divided by FPS, and that will run only once. Timer mode is once. We use this the first day, which is what we use to define how the when we implemented the cursor movement that had a gizmo defined inside of it, we use the timer mode. This has two timer mode. It has once and infinity, if I'm not mistaken, repeating here, right? So that's how it works. So that's basically what we are doing. So we are saying reset the timer frame and start counting all over again for every frame time once you increment. So that's basically how the animation works. So let's look at the last thing before we make wrap this as complete. If you look at the trigger, the last thing we have here is execute animation is understood, right? The next thing is the trigger animation. The trigger animation in this case does something similar as well. Now, what does it do? The trigger animation does similar to what the execute animation does, but in this case, execute animation just runs on 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 um on every keyframes, right? On every render of the frame, right? But trigger animation is actually on demand. So that means all the times I press the key here to execute any of the sprites, that is handled by the trigger animation. So that means it is triggered. So the trigger animation is just a function that takes in S, right? S is a component, and then it takes in the animation and that's the animation configuration. It takes in animation whereby we want just the animation configuration with S. That means whatever is passed into it, and whatever is passed into it here is just the sprite that we defined on it. So that means in this case now we create a new timer when the animation is triggered. And what does this do? That means we simply create a new timer whenever we trigger any of these key. That's whenever we pass in a component. A component in this case is right sprite or left sprite. How do we know that? Because we define a component here, left sprite, right sprite. So we can pass in a component to this function, and then we can run it just if you just press any of this button. Left, if you press the right key, right? Run if input just pressed is right arrow key. You can see how this literally translates to English, but it's just a function that does something. So if the key press is right arrow key, trigger this animation. That means we trigger the right sprite. If it is left key, trigger the left sprite. And that's it. That's basically what's happening here. But the bulk of the work, what makes the work easy to understand is the animation configuration we define, which is timer from FPS. Which timer from FPS means you are simply returning what? A timer instance, which is something like this. And that's basically what we are doing. So that is all we've been trying to understand for some time now. So everything we see here, let me execute this again because I've changed some things from it. Now the first thing that runs on start of this app is the execute animation. What works when I press a key now, that this keeps moving now, is the trigger animation. If I click on this again, is the trigger animation. That's for the right key, and the other one by the left for the left key. So what that means is what handles that execution is this timer from FPS. It simply means that whenever you run this function, you are starting the time again. Remember we said you are creating a new time, you are passing the duration of it to be 1 divided by the FPS, and then you are setting it to the timer. Remember the analogy of people doing laundry and one doing dishes. 4 dishes and 4 people's laundry. They are two different things. One is going to take longer than the other. How do you define that? You need to define your execution by the number of time that you have. So let's say both of them have 30 minutes. In this case, you have 30 minutes, right? So that means you need to divide your workload by the number of, define it any how you want to do it. For the person that wants to do just 4 dishes in 30 minutes, you can just divide each of the plates to wash by 30, meaning it has to do 30 minutes. So you can say, okay, I'm going to take 7 minutes for each of the laundry, each of the plates I want to wash. Since it's just 4 plates, I will take 7 minutes to wash each of them. But the person that wants to do laundry for 4 different people with, let's say, 10 clothes each, right, needs to divide it into maybe each of them and say, okay, since you guys have 10 clothes each, I'm going to wash 10 people's clothes first. I'm going to wash 10 clothes first. I'll put 10 clothes in the washing machine. I'll execute that in 7 minutes. I have to time myself. Now, that timing yourself is exactly what is happening here. We are timing each of the tasks we do. So in this case, we are creating a time here. But how do we do that? We divide the frames per second. Let's say we want to do it in 2 minutes. In this case, if you want to take 30 minutes, all we are going to do is that, okay, and do that, divide it by 1 second, because this is more like, we are saying you are working with frames per second, not per minute. So in this case, we are dividing per second. So we are dividing how many frames we want to render by 1 second to get the actual time that is going to, we are resetting the actual time that is going to take for that animation to render. And we are saying that once you do that, we are creating it as timer mode to be once. The way this thing works, just imagine it in respect to time. But initially, you might not really need to understand the calculation much. Just know that when you want to render something like this, you probably need to render a timer on whatever you want to do to get it to work, run per frame majorly. But the analogy and the definition and the calculation here actually makes sense because it is 1 divided by the number of frames per second, which in our case, if I'm giving you a task to do in 10 seconds, you want to divide it by how many tasks you have by that 10 second. So in this case, because we are running it frames per second, that means we need 1 second and divide it by the number of frames we want to execute and start that as a new timer. So once you start that as a new timer, you're telling it to execute just once. So that means on demand, when you trigger this function, you are executing a new timer with the number of tasks you want to execute in that second. Or the number of frames you want to execute in that second, which is what we did here. We want to render the sprite in 2 seconds. In a second, right? Six frames in a second. We divide that 1 by 6 in this case. But we want to render it not in 6 seconds, rather. We want to render 2 frames per second. So in this case, now we have 6 frames. So we are saying that for each of the 6 frames, you have to render it we have to render it 2 frames per second. We have to render it 30 degree of a second for each of the execution of a single frame. And that's exactly what is happening here. So that means for each of the frame per second now. So that means if you count this now, you're going to take 1 and 2. It's going to take 2 seconds to execute the entire thing from start to finish. So it's going to spread of that task into 2 seconds. Into 2 seconds. That's 2 frames per second. So it's going to execute all of the frames within that 2 seconds. In this case, we're executing this 20 times per second. Do you understand? This took a second to execute the entire thing. This took a second also to execute this, but 2 frames per second. This one ran in 20 frames per second, so it becomes faster. Everything that happened there is a second. 1, 2. So that's basically what happens here. So the whole idea of frames and timing can be a bit tricky. Time is literally something you don't really want to wrap your brain around because timing is difficult. Time is a difficult concept to understand, but that's why you need to dwell more on it when you start, because that's why every engine provides you the ability to work with time in a simple way. And you can always get examples online or get unblocked because it can be confusing, but you don't really need to work on it from the granular level most of the time. So yes, that's basically it. That is for the animation. Now, time to go back to this because we've done all of this, right? We've spoken about this. I'm going to leave that increased. So that is how this was implemented. And now we understand how animation works. First of all, what you need to do is you need to have your sprite. You convert that sprite into a texture. You convert the texture into a texture asset layout or a texture layout. That means you break it down into grids or somewhere where you can store it and access it. So that's your texture layout. And when you have the texture layout, you now need to define an animation logic for it, meaning that you convert it into a loop that runs for a certain number of time. And that means you need to have a timer, and the timer starts immediately you want the execution to start. In this case, like this, we initialize our timer to start running from here. And then we define the logic for how it's going to run. In this case, we just need to increase the index of the frame from 1 to 6 or 1 to 10, depending on the number of sprites that we have. And that's basically how animation is done, at least for simple 2D animation, 2D sprites. This is basically how it happens. So we've taken a bit of time explaining this, right? But like I said, we are working with 3 things today. And the first one we've concluded, and that was why I had to start diving into it from early on at the beginning so that we don't need to spend more time or waste time. Now, this is the second one. The second one in this case is just a sprite that keeps running. Now, I believe that we can think of how this works. We already have an idea, so we don't need to think much about it. Renders an animated sprite by loading on animation frames from a single image into a texture. Understand all this analogy and changing the displayed image periodically. So if you are to think about it, how do we do this? It's actually even simpler than the first one. Like, it's literally simpler than the first one. The first one, we had 2 things. We had a trigger, a custom trigger, a manual trigger, and we have an execution that renders at the first instance of the frame. So how do we run this? Now let's implement this to make it make sense. So I'm going to implement this two, right? We already have this two that runs 2 frames per second and 20 frames per second, right? So I'm going to add it to the left arrow key to make it make sense so we can understand what is happening. So where is the text? We rendered our text here, right? I'm going to add this to it. Left arrow, animate left sprite 2 frames per second FPS. That's the for the first one. Then for the second one, which is when you press the right arrow key, 20 frames per second FPS. No, did I press per second? So I'm going to add this here. FPS. Okay, so if you go back to run this, restart this. Okay, let it come up, let it come up, let it come up, let it come up, let it come up. Cool. Nice. So now we have this defined, so it makes a lot more sense looking at it like this. The left arrow animate left sprite 2 frames per second. So that simply means we can see the animate left sprite 2 frames per second, animate the right sprite 20 frames per second. So if I click on this, you can see this, how fast it is. And this one keeps catching up. So this is like the tortoise and the air story. You can see the gap between them. I just have to make it like that. So I want to do something else just to make it a bit fun. So it looks like one is running faster than the other. So the one on the left, let's reduce this by 4 and then run this and let's see what happens. This is just being playful. Actually, at the end of the day, we are building a game. So it makes more sense to make it like this. So you see that we've reduced the scale of this by reducing it to be very, very small. So it looks smaller than its counterpart, which is the one running. So it gives this perception of depth, like one is beef, one is far ahead and the other is slow. So what we can do to make it even more intuitive is we don't want this to be too small. So it won't look like it's too small. We can't see it. So we can double the value, right? Currently it's just at 75%. Increase. This one is 75% larger than that one. So we want to make it 100% larger. So what we're going to do is I'm going to make it to give it that perception of depth, a very, very high perception of depth. You can do that and you can do this. You can see, so it becomes a bit bigger. This looks closer to you, the user. You seeing it from far. It looks like this guy is faster than this. So another way you can do it is you can make it look, you can actually add lighting to it, to maybe somewhere here, so that it gives that perception of, oh, this guy is running towards something. We can do that, but I don't want us to waste time doing that now. We can always do all of these things as fun experiments when we are done with the schedule for this particular series. Then we can take that as certain examples you can implement, build, have fun implementing and executing. That is something we can do. We can add the bloom, this bloom implementation we have here, and all we need to do is we can simply copy. Okay, I'm not going to do that, right? I don't want to, but it's something we can just do. We can implement that in the camera just like we do here, and do the same thing for our sprites. Where's the camera setup? The same way we have the camera spawn here, we can do the same thing here by adding the tone mapping and the data here. But basically, what we want is the bloom, right? We don't want the bloom. That's all. So we want the bloom, but we need tone mapping also to enable that work. And but we need the band data, which is optional, but it still works. So we can settle for these two. We can copy the three basically. I said I don't want to do it, but I feel like doing this. So we can do this. We can spawn that. What did I do? So we have this, right? We can spawn this. But then the reason why I don't want to do this is because we need to configure most of these things, especially the bloom, and then define. Oh no, we need to define the bloom like this, and then we need to define all of the things that happens to it in terms of the frequency and high pass and all of those things. But basically what we need to do first of all is add it to the transformation. We need to define the mesh first that wants to define that too, which is in this case the circle that we define first of all, and then we define the bloom on it and all of those things by passing a color to it. So we can do the same thing actually. Let's do this. Let's do this. let's create another one of this. So we are not just spawning that, we are spawning both before the text. Let's add it before the text. Create a circle mesh. So we need to create a mesh type here and add the mesh. Trying not to waste time on this, but let's see if I can get this done in less than 5 minutes. We need to also create a material mesh also and add that here. Then we need direction right. No. Oh, okay, that's import this, but it's not, yeah, it's not public, it's just private, so we can't use that. No, we don't need this. We don't need the direction, so we are not going to use it. So we only need this spawn. We're just going to put it in a very far location, maybe like 800. Or let's make it 800, and let's make the Y. Let's make it. Let's put it at the top. Let's make it 100. Z should be what it is, so we can translate it to be at the top. We still use the yellow-like color, so it becomes bright. And then the next thing we need to do is to add it, just like we did to the spawn. We need to add it to the circle, right? We need to do that. We already defined the color. Now we need to add the intensity of the bloom to make it, to give it that perception of what we are trying to implement. So that's basically what we're trying to do. So in this case, just like we had the hexagon that was defined, we need to add that to the bloom. So we are matching the bloom, but in this case, we're just defining the which of the property intensity. Yes. So we are defining the intensity on what? Oh, now this is where we need to implement this. No. Okay, so we can do that. We can do that. It's not going to be complex. We need this. First thing we need to do is we assume that bloom is already going to be inserted by default, which in just the same way it was removed yesterday or added automatically. So in this case, it's going to be inserted by default when you press the space key. So it's going to be inserted. When was it inserted by default? I'll just assume that it's already on it because we already defined it into the camera. I don't want to copy this because I don't need the entire thing. I can copy it and make some changes to it. Yeah, some of the things we don't need, like the tone mapping, for instance. I don't even know why we added tone mapping because we don't really need it again. So yeah, this is just me like doing a lot of zoning out into something else entirely. But then I just want to show something first of all, and that's the essence of me doing this. And what am I working with? Where is it again? Intensity. Yes, this is intensity. Bloom dot intensity dt divided by 10. There's a default intensity for it, which is no, not you. There's bloom here. Bloom comes from here, which is defined on this as on camera. How can I enable this without creating something else entirely? Okay, I need to create something else entirely because it doesn't work. Okay, you know what? I'm going to do this. First of all, I'm just going to do this. Let's not waste time on this for now. Yeah, we need to render the camera because we not define what will happen on updates. So it's not going to render that. We'll just spawn it. That's what we did. So we need to create this. Something simple, similar to this, and define our camera because we need to define that. Yeah. Okay, so let's do this. To mapping entity. Do I need all of this? No, I don't need all of this. What's the best way to implement this? Okay, let's try something fast. So we are updating the bloom. We are going to add all of this to it. Just trying to be fast here. Oh my god, what did I do? So we are going to define the camera. We are going to define this here. We are going to take the bloom. So remember in this case, we did the insert here, which is the camera entity. We need to define command. Crazy stuff. No, that's not it. What syntax am I writing? It's camera the entity. Plus insert. What else do I need? Defining the bloom. Okay, because you don't need to change any of these, since you don't need to update it, you don't need to define the time that changes it. I think you're good to go. I guess so. Nah, this seems like it's missing a lot of things. Okay. Oh no, it's not added on it. Okay, yes, there's still a lot of things, like I said, that we've not done, which I cannot understand. No, let's see. What am I missing? Core pipeline, prelude, process. I feel like I'm missing something here. No, I know there's something I'm not adding, which because I don't want to like do all of this. Yes, I understand that. I'm just trying to see if I can hack my way into making it work. But definitely not. It's going to take a lot of time to do that. I don't know not a lot of time, but there's no waste time on it. Let's go because we have two more things to do today. That and the 3D, which I'm trying to make sure we implement as well. So after defining that, insert the bloom into it. No, why? Why I made a mistake somewhere? It's not that. Okay, so I think this gives you a sense of what I was trying to implement, even if you didn't do it, but you understand what we are trying to do. So what we're trying to do is to create the circle, render the circle, which we did have here. So what we did yesterday was to set up that, then update the bloom setting, which was where the shape was being rendered. Right, we removed with the camera this on the text, and we add that everything happened here. Oh yeah, not you. Everything happened. Yeah, because after we created all of this, we created our text, we created a circle. Oh, I just knew it. It should be there. Come on. Wow. I'm just imagining why. Okay, I think I know why. Because I made it a bit too far to the right. So it made it. Okay, I'm just going to reduce the direction. So all we did was just insert it. That makes a lot more sense. So you can see what we did, right? So it's there. It's just there by way too much. So I made it a bit far to the right. I made it 400, which should, the reason why I made it 400 was so it's not too close to the position of the other one, which is minus 400 or 70 or 400 should be perfect. I was thinking I made it minus 400, so we can make it a bit more on the y-axis, go upper on the window, right? So it doesn't appear here. So what I can do is not just increase we can increase the intensity of the we can increase the intensity of this by saying bloom dot no, no, that's exactly not what I'm trying to do. Yeah, actually that's exactly what I'm trying to do, but because we are trying to match bloom here, right, so that's as kind of like destructured it. Yeah, but doesn't matter, we can still do it. Unwrap. The intensity is going to be, I'm going to make it dot 65. Yeah, so that should make it a bit brighter if I'm not mistaken. And yeah, it should not be far to the right now. I was just looking at it that this should work. So basically, you see what we've done so far, right? We've, in just few minutes, we've been able to add the, yeah, like this light source to look more like sunlight appearing on them, kind of like to give that feeling. So obviously we can't move it now, but it gives that sense. So if we have to do it now, because we can actually add shadow to it. If we are rendering it as a 3D object, we can add shadow to it, which I said we're going to look at today. So we are still going to look at that today, but just remember that this is what we are trying to do. So we can do this, make it feel like they are running towards something. So in this case, they are running and there's sunlight. We can make it look that way. And also we can make it, you can change the color from, I mean, in terms of the color of the camera currently, which is just here's the setup again, which is just in this case the camera is just plain, but we can make it have a color not like black but a bit more whitish, something of some sort. You can copy that from the camera configuration here to give it a color, and we can do that by giving it a color of I don't want black. Let me see if I can give it white. Yes, let's see what happens. Since there's a light source, let's see if there's anything reasonable we can pick from it to give it a bit of more artistic feeling. Remember what you are seeing now is just basic gaming structure. We've not gone into some intermediate stuff at best, but now you can see this. Of course, the sunlight is there and the view is there, and it's a bit too bright, yeah, I think, for people that are watching it. But it gives you the feel of there's sunlight. Yes, they are running in sunlight, something like that. Okay, I think the 2 frames per second is way too slow. I'm going to increase it from 2. I'm going to give it another color. From 2, I'm going to increase it to like maybe, let's give it 10 that it was before, just to signify what we are trying to do. And then you guys can see how this is playing out, right? You can see how all of everything is just playing out to each other. You can see the movement, you can see the color, you can see the changes, you can see it's trying to simulate like we have a sunlight. Because all of these things we are writing ourselves, right? And we are making use of actual Rust concepts. We are writing our structs, we are implementing our structs, we are writing functions, we are actually writing code in Rust that displays and creates this game like view. Right, that's what we are doing. So in this case, now I'm going to run it again, giving out the sense of that perspective. So I'm going to make it feel like both are running, 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 even though the one at the front is way faster than the one at the back. And it gives that feel that they are running. Now, if you want to convert it to an effect, you can give it an effect whereby the road is moving and it's just moving to the left. And it gives them that feel that they are moving and they are running. That's basically how every game you've seen is. If you look at this Chrome game that you play on your mobile, that whenever there's no internet, you see jumping, all those that jumping dragon or jumping bird game on Chrome. This is literally what happens. There's a you can look at it like a sprite also that is defined, rendered for that particular image. But because it is just one, you don't need multiple sprites rendering for different frames and changing the index in this case. So you are doing something like this, literally. And aside from doing something like this, also you are making it move, right? But you are moving the screen, you are moving the background, right? Which is the one with the obstacles that if that particular guy jumps on, it fails. In this case, we can create something like that eventually. But for now, let's look at how to render, make it continuous render, not just a frame by frame render. In this case, like what happens here, that it just renders once and stops, right? So we are going to come back to this and we are going to like tweak it to make it work. And that's like what we always do. Like what we did yesterday, we picked three examples, merged them into one, and implemented it. Today also we are going to be doing this. We are going to be picking three examples, tweaking it, and adding it to one. Make sense? Yeah. All right. So basically, this is what we've done so far. So I hope you guys can do something sheet, sprite animation, and with interested in this, you can begin they are learning 3D concepts because we are building a game here and we're going to be building a very, very interesting game at the end of this series. But until then, we are going to be building little concepts that we can pick from to build and become one eventually. So, like I said, if you have someone that is interested, please share this video with them. Let's so they can also learn. Right? I really appreciate that from you. They will appreciate that from you, and also appreciate you sharing to them because we learn, we grow. That's how we behave here. So yeah, that's basically it. The next thing to do is we've already executed this. It looks nice. It looks cool. Next thing we are going to do is let me change the text. I want to change this text from 2 to 10. Okay, I'll change it to 10. So now let's go to the next thing I want us to work with, which is this continuous running, because it's not cool when we have something like this that they just run once and stop. This is not what we want to implement. Far from it. We don't want to implement them to just run once and stop, right? We want to give a feel that they are running, more like a marathon. So we are going to do the same thing.
It's 18 hours.
We are going to do the same thing in this case. Yeah, it's 18 hours, I know. So now, like I said, this one is far easier than the one we just implemented, right? So what we can do is we can create another sprite that keeps running, blend it on top of this one, so we can see the three in action. So we are going to look at the code. It's quite similar to what we've just done. The difference is that this is a continuous running animation, different from the first one that we created that just executed on startup or on the first render, and then you can trigger also. In this case, you can't trigger this to run, it just keeps running continuously. So how do we do that? The first thing we need to do is create our animation indices. And okay, let's not start with that. The first thing is we create our main function. We define our main functions, everything we need. We set the image plugin to prevent blurry sprite. We set our startup, which we define a function for on setup, and we understand that the setup is similar to what we have here on the setup here. In fact, this is more complex than this one, like I showed you guys just now. So what do we need to do? Let's look at it simply. Next thing is similar, right? The first thing we have in our setup here is we have the commands, we have the meshes, we have the material, the server, and the texture atlas layout. The same thing happens here: commands, assets, and texture. In this case, we don't even need more like the meshes and the material. We don't need the meshes. The reason why I had the meshes here is because I was creating that sun like that you saw there the other time. We don't need it this time around. So um all I needed to do was just use this directly. So we don't need all of those. So sorry, excuse me guys. Just give me a minute. Okay, 1 minute. I'm back. Yes, so next thing, let's look at this and to see the difference and to see how we can add that and add it to our existing implementation. So what do we need to do? Basically, we pick the same thing, which is the texture, based on what we've implemented so far. Nothing too crazy, nothing too different from our setup. Remember, from our setup, we created the camera, right? We spawned the camera rather. In this case too, the camera is spawned. You can see from here. We spawn the camera, we spawn the sprite. But before we do that, we defined all the variables here that we are going to need. Similar to what we did here, we define our variables, the texture atlas layout, the animation configuration. But in this case, we do the same thing, but a bit different. We define our texture, which is still Gabe. Remember, Gabe is what I'm calling them Gabe, like I said. So these are Gabe or two Gabes. Okay, they are this is Gabe. They are just two different instances of Gabe, right? This is Gabe, this is Gabe. So the name Gabe is what we are working with here. So we have Gabe loaded here as a texture. We have the texture layout defined, but in this case, the same thing. The same thing as what we have here, which is 24 vectors, 24 size, 24 pixels in size, which is what we define by the UV2, UVEC2 sizes by 24 by 24, since that's the size of the sprites themselves. Then we define the number of columns, which is 7, like based on our explanation from here, which is 7 different frames, right? 7 columns, 1 row, 7 columns. That's basically what it is. So in that case, we are doing the same thing here. We define the size as 24 by 24 pixels here. We are loading that into the grid, creating a grid from it. For it, we are not setting any padding to it because there's no need for a padding, and we are not setting the offset. There's no need for the offset. So the next thing we do is define the texture atlas layout, which we add the layouts that we defined to. So we do that by texture atlas layout, which is what we defined here as a resource, as an asset of texture atlas layouts struct, and then we add our layouts that we defined. The layout here is just a grid of 24 by 24 pixels, 7 frames, 1 row, 7 columns, 1 row, right? That's basically what it is. Similar to what we did here. Literally the same thing. You can copy this and use it, which is why we are not going to rewrite the same thing. We're just going to be making use of it, but extending it. So the next thing we do here is we now define. Now this is the difference here. The difference is that we define something called animation indices. The animation indices is what they created here. You can see it here. The animation indices is created here. It's just a struct that is defined as a component, which is similar to the struct we defined here for ourselves as a left sprite and right sprite. But in this case, the defined animation indices that define something similar to this. Let me show you the animation configuration. It's the same thing, literally the same thing, but this is more extended, or let me say this is a bit more defined than the animation indices. You can see it's literally the same thing, the same type, the same field, right? Just different names, first and last. In this case, too, we have first sprite, last sprite, same U size. You can see it. So that's the main difference here. And that is because in this case, you just define the animation indices to be first one is 1 and the last is 6. Remember where we did that also? We did that in our setup, something similar, which is what animation the new 1.6. So we can literally use the same thing without even creating animation in this. Just reuse this animation configuration and it still works the same way. So now that we have gotten all the texture definition out of the way, the next thing we do is we spawn the camera, which we've already done. But in our own use case, we spawn more than the camera. We spawn the tone mapping, we spawn the bloom. We don't need the tone mapping actually because we are not using it. But we spawn the bloom because we needed it. We spawn the camera configuration to give the color a background color of white, which is what we use to get this color that we have here. We can use blue, we can use black, we can use anything. It's just I just use the white so you can give that concept of daylight, right? Exactly. And we can also convert it to look more like a night picture, kind of that they are running in the night, stuff like that. All still the same thing, right? It's just configuration and definition. However you want, you can tweak it as you want to. So the next thing we look at is the command, we spawn the image, right? Now, this time around, we are doing something a bit different. Not different in a very crazy way. It's literally the same thing. Remember when I talked about we creating this, where is it? Let me look for it once. Yes. When we define the timer in the animation configuration, when we define the struct called animation configuration, and in the struct we defined an implementation. We implemented the struct, right? And then we defined the timer from FPS that I was explaining the other time, just minutes ago, about how this is run. But I mentioned that we have the timer mode, which is what we use to create the time to run once. In this case, we have it just once. But what if we change it to repeating? Just saying, without changing anything in this code. Just this repeating. Now, what do we have? Does it do anything to our code? Does it break our code? Does it affect our code in any way? Let's see. And then we have the same thing. So literally what we have been trying to do now, what we are looking at now, we can see it here in action just by changing one particular thing. That's it. But that doesn't still mean that I can't still press the. You can see that whenever I press the keys, it freezes and then it continues. If I press the right key, it freezes once and continues just once. The reason is because I started the frame again and doesn't even affect it more than that because I set it to continuous, not once, or to repeating rather, not once. And that's it. So we've successfully created the same thing they're trying to do. That's why I say this is even simpler because we've done the hardest part of having the manual trigger. So we can manually tweak our trigger in the sense that whenever we do this, we don't want the timer to just continually be repeating. We can change it from repeating to once. But we don't want to do that in this case. In the case of this example that we are trying to implement now, we want it to keep repeating, like keep running. So it gives guys are running and running after each other, and it gives that illusion in a very simple way that makes sense because now this guy feels like he's running to catch up to this guy. I don't know what we are trying to do. So successfully we've done two examples and combined them into one. We took the other example. By the time we got to the simpler one, you see how it was able to we were able to work with it to make sense. All I did was just to change one thing from the previous one to get it repeating to work continuously. So that means it's literally the same thing. Now let's look at it to be sure that it's the same, and I'm not just performing any strange thing here. Let's go back to the setup. We've already defined the texture and the camera, right? Now we also need to spawn the sprite. And where did we spawn the sprite from? Here. No, here. We spawn the sprite from here. We have the image, which is the same thing with what is here, the texture. But in this case, we don't call it image, we just call it from Atlas image. But in this case, we call it sprite. We define that sprite, and we don't define it from this. From Atlas image is like a function that is implemented for sprite, similar to how we did this implementation of timer from FPS. Because if you look at animation configuration, look at how we used it here. You see something similar to that. So that's the same thing they did here. From Atlas image exists on Sprite. They define the texture Atlas, similar to the same thing we have in texture. As you can see, image texture atlas with the same configuration, layout, and index. And in this case, layout is the same thing as texture atlas layout. Index is the same thing as the first index, which is what we defined here. And then we specify the default. We unwrap the default. Let me call it that. Basically what they did, but they didn't even need to unwrap the default because they are mainly calling this like specific function to use. And then they call the transform on it. The reason for the transform is so that they can scale it just the same way we also scaled it. But the reason why they didn't use the translation here is because they did not need to translate it anywhere on the app or on the viewport. Actually, it was not needed. So all they needed was just one part. Since it's just one image, there's no need moving it left or right. So you can see. So we've already implemented the other one. Then we called it the right sprite. In this case, they call their own animation indices. The reason is because they only need the animation indices here. They don't need that. And then the animation configuration. The animation configuration is what we've already defined in our own use case. Animation indices here is what they defined here. Then they defined an animation timer, which we already defined from our animation configuration itself. Animation configuration is coming from animation config, right? So by adding that here also, we already automatically have access to the animation indices. We have access to animation timer rather, because if you consider it, our animation timer comes from animation configuration, which is what our timer from FPS, which is the same thing. We create a timer just the same way they did. They created a timer from second. We also did the same thing. We created a new timer instance. First of all, we created a duration from it from seconds F32 in our own use case. You can see how more complex this example is. So if you can fully understand this this is a simpler approach to implementing it, and it just works. So we created it from 1 second, and by 1 second we mean that we create it to be 0.1 second. But in this case, we are creating it as 1 second divided by the FPS we define. So that way we can that means in our own explanation, there's no way to define FPS for this particular implementation. It just keeps running at 0.1 FPS. But in our own use case now, we can define the FPS because we make the implementation dynamic. So that means that's why we were able to achieve this slow and fast pace. Look at it, you can do we can, right? We can do that. But this guy is running faster, this guy is running slower, and it's actually, and it feels like the sun is beating both of them, right? It feels like they are running in the sun. So that's basically what we are trying to implement. I know it seems it seems kind of simple when you look at it now. Is this what we've been doing for past 2 hours? But then you see how the pieces are coming together. You saw how we were able to blend what we learned yesterday with today's lesson, because this was not part of what we built. What was in the example that we learned? The example we learned today is this. This is what we try to do, and we change this from this. We change it to this. So you guys, so you see this now. So we change that from a still frame to a repeating frame that gives the illusion of, oh, we have two images running. Don't forget, this is just PNG. This is a PNG, right? This is an actual image. It's an actual image, like I showed you guys. So we gave the illusion to the user that, oh, there's a guy faster than the other guy, which is this guy is faster than this guy. Even though this guy is running to catch up, this one is too fast, and this one is behind, and they are running in the daytime. That's what we've built so far. So what we did was to convert something like this to something like this by converting two examples. We converted what we did yesterday, right? We turned it to this, we combined this, and we combined what we did yesterday. So we combined three lessons into one to form this. But we are not done. We still want to do one more thing. We want to implement the 3D before we leave this, because that's one of the things. Those are the three things we said we are going to start today. I know I can push this to tomorrow, but I want us to start it today because it's part of the plan, so that tomorrow we move from there and implement more features on the 3D image. So this is how we are going to be building it for the next few days until we are comfortable building a game like this, and then we take up a major project to work on. It's a way of learning, and it gives us that sense of, oh yes, we understand what is happening here. So if we want to add more things, we can add other things like stars all around, convert it to a night time, and add like stars all around by making a for loop of different images and scattering them randomly. That's possible. So we define that and they scatter them randomly. Right? They are running at night, but we change it from yellow to a bit of white color to give the illusion of the moonlight. All of these things are possible. It's just tweaking this, configuring this, adding a simple function, and we can make it work. I hope this makes sense. So that's basically what we are trying to do here. So now the last thing to do, now if you consider the example, you can see this. So this is quite easier than this, and that was why when I changed it to repeating, so that it just worked once, because that's what we needed to change to make it start running concurrently and running forever as long as it exists. So this is what we are trying to build. So we are trying to build this, and I think we've done justice to what we wanted to do. 75% of it. We said we are going to do three things. We've done three things, two things rather. We need the last one. Actually, we've done three things, but we want to add one more to it, which is the 3D that I said we are going to start yesterday. So going back to the 3D, let me go back to the actual examples. So I said we're going to touch on three things yesterday. We're going to touch on the sprite animation, the sprite sheet, which we've done. So we've done the sprite animation, the sprite sheet. We need to do one more thing, right? Which is what? The 3D scene. So we need to actually create a 3D scene. And now we can create something like this, the atmospheric fog, and blend it with this to make it a bit more reasonable. Like they're actually running in a world where there is sunlight. We can add the sunlight, we can spawn the sunlight, this kind of thing to look like a sunlight. We can spawn it alongside this scene. Remember, everything here is configurable. These are just backgrounds. Then the light is just like everything we created here. But you know that it's a bit different from what we did here, because this is just like a circle that has a lot of things. We can actually make it a lot more different by changing from, let's modify this a bit. From changing from just the intensity, we can change from the intensity to something else. What's the name to use? We can change the high pass frequency. Is it high pass frequency? Yeah, let's change that to maybe like 0.65, if I'm not mistaken. Value used after being removed. Oh no, no, I'm not trying to move it. I'm not trying to move it. What am I doing? I'm trying to move it. Oh, no, 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 no. Okay, so I need to. Oh, jeez. I need to create a reference to this. I don't want to use this completely. I need to create a reference to it. If not, we won't be able to use that. And I don't want to clone this. Yeah, yeah, I don't want to clone that. I need to create the trait for it. Ish. No, 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 no. Don't let's do this. Don't let us do this. I don't want to clone this. Okay, so let's look at this. Let me show you what. So I don't want to clone that. The reason why this is happening is because of this guy. Value is after being moved. I know it's been moved. Don't want to use this. Nah, can't use this actually. It's not going to work. Okay, so I wanted to add the. I wanted to add the other one. I can't use the muted. I can't use this. I can use that actually, but then nah. Let's see. How do we do this? So I already have this, and I can create a reference to it. That's the only way I can use it multiple times by creating a clone of it. Yeah. Value moved here. What do I don't want to move it? I want to. Okay. I knew that was going to be crazy stupid. I don't know. I'm not going to do this. I know this is crazy stupid. Colin cannot move out of this, which is being a shared reference. Exactly. Cannot move out of Bloom, which is a shared reference. Exactly. I understand that. And blah 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 blah. Doesn't wrap. Yeah, same thing. This is just going to be terrible. Okay, no, we're not doing this. So I'm just going to leave this as it is. That's- This this is where we begin to have issues with borrow checkers ish. So I need to unwrap this actually. There's a way to do it, but then it requires me to like pass this, remove this. I'm just trying to look for a shortcut. Sorry about that. The guy we say we actually like digress a bit, but you get the idea. So the next thing we are trying to do today before we wrap up is so this is what I want us to do, but this will be done tomorrow, right? So you can see all this 3D view you see. You can see the lighting source, you can see the light source, you can see the render, the shadows that reflect. We want to do something like that to our animations here. So the essence of me creating this sunlight here or simulating this sunlight is so that it can give a sense of a shadow. So you can feel like this guy is far behind. It gives that perspective currently, but it doesn't give it enough the way I want it to be. So I have a standard I want to meet for this animation, but it doesn't meet it yet. But I'm not going to do too much on it to make it meet it. Reason is because I want us to make it look this way and stop there. But like I said, we are going to finish with what we started with because we decided to do the 3D scene. So we are going to continue with the 3D scene. So after that, we stop. Then we continue from where we stopped tomorrow. The reason why I'm starting the 3D scene here is because we need to, I want to give us an intro to it so that tomorrow we know we are going fully into 3D. So I want us to have an idea of the difference between the 2D and 3D the same day in the same example. Then before we move into the other one, you can see it's quite simple. It's not really difficult. Like it's like it's simpler. It's shorter than, let me not say simpler, but it's kind of like as short as this single implementation. In fact, this is even longer than it. Consider this. You can see it's quite short, like literally very short. And we don't need to do much. All we needed to do was just to add the setup, because we are not updating anything. We are just setting up a 3D scene with light source and reflection. That's all. So I want us to do this today. Then tomorrow, same time, I'm going to create a same time. So if you want to if you want to be notified about the time tomorrow, it's not going to change. It's still going to be 4 p.m. West African time. But if you want to be reminded and notified, consider subscribing and then turn on the notification so that you can be informed, right? So I really appreciate that also. So it gives me a sense of, okay, someone is learning from this and you guys are actually learning something from this series. So that's basically what we want to do here. So yes, back to implementation. So what I'm going to do is simple. I'm going to try adding the 3D component into our two. Okay, no, that's a stupid idea. Reason is simple. I'm going to show you what I'm trying to do here. Okay, you know what? Let's try something, right? So we already have our 2D sprite and 2D sheets, animation and sheet configured and done. Let's go to the 3D scene. I'm trying to implement the 3D scene. Remember I said something about the 3D when I was saying something earlier today, that we need to, when we are working with the cameras, when I was spawning the camera, I said you use the mesh 2D for our um 2D scene. We use the camera 2D for our 2D setup to spawn the camera for our 2D world. And when we want to spawn a 3D camera, we need the camera 3D also. We don't use the camera 2D for spawning or for creating our 2D world, or for giving us the sense of, okay, lighting and all of those things for our 2D world. So for the visuals for our 3D world, we need an actual 3D camera setup, which is what we need. So that's what we are going to set up. We are not going to be working with the 2D camera here anymore. You can see the difference here. We're working with the 3D camera, not the 2D. So considering the camera setup here, you can see this is spawning the camera, but in this case, it's not camera 2D like what we've been using so far. It is actually camera 3D this time around. Let me show you. Where's the setup? Yeah, you can see camera 2D here, but then it's going to be camera 3D in that regard. So for now, we are going to create a new one. So I'm going to create a new file and call it what? 3D. Nope. What am I doing? Call it 3D what? Writing 4D. I feel like creating 4D. 4D aspect. We are not creating 4D, just 3D sense, right? So I'll call it scene 3D since we can dots 3D, attach it to the module here. I'm not adding that to Git. So what we are going to do basically is copy this, or basically let's copy it since I don't have to do this. Copy this first of all, copy this intro, right? So next thing we need to do is create our setup function. No, I feel like we should just write it, just to give us a sense of this one is already giving us what we want. All right, you know what? I'm going to use this, but even though most of the things here don't exist, cannot find 3D in this scope exactly because it didn't import it. What did you do? Okay, do I need the asset? I don't need the asset server. I'm not importing any asset here. Come on, it's reasonable. I need the materials, which is yes, materials, yes. What else? What's PR bundle? I have no idea what PR bundle is. I'm just going to assume it's correct. All right, yeah, let's just focus on this, right? I don't know what PR bundle is, and you are not importing what PR bundle is for me. Okay, enough of this. I'm not using this anymore. Let's just take it back. Let's create our setup ourselves. Right? I wanted it to thinking it's going to give us something important. But I want us to write this ourselves for the simple reason of understanding the difference, right? I don't want to have to explain everything. I want to be explaining just as we are moving on. So the first thing we do is we create our commands, right? We create immutable commands, first of all. We create our immutable meshes, second, because we need the meshes and the material. Because we are trying to create what we're trying to do is set up a 3D scene, a simple 3D scene with a cube. So we're trying to set up a 3D. I'll call this, so I'll say a 3D scene with a camera, a light, a cube. Okay, let me just use that. That makes sense. So that's basically what we are trying to do, right? Perfect. Yeah. So we have the commands. You know what we use command for? We use that for spawning whatever we want to do. We need the meshes for defining our 3D components. Meshes, we use the meshes for defining our shapes initially when we are working with 2D. Now we are working with 3D. We need the meshes also to create our 3D shapes. Now we are not longer creating flat shapes like squares, circles, polygons, and rectangles. Now we are creating things like cubes, cuboids, cylinders, donuts, and also circles, but in this case, like spheres or 3D circles, 3D spheres with depths that you can rotate and you can see all of those things. You can create all of those shapes now, right? That is what we are trying to do. Parallel, we are creating things like complex shapes now that have depth, breadth in this case. So now that's what we are trying to do. So we've defined all our assets. We don't need the asset server. Why do you keep giving me asset server? Also the materials, we don't need that. We need the standard material, not color material, not flags. We need the standard material from the assets, right? Materials. So we have that already. So what's the first thing we need to do? We need to implement our spawns. Let's spawn the camera. Let me just call that circular base. Okay, fine. Let's start with the circular base. Nope, I prefer to start with the camera. I prefer to start with the camera. So we do the commands, the what? The spawns. We spawn our camera. In this case, it's going to be what? Camera 3D. That's the first thing we want to spawn. But before we do that, what do we need to do first of all? What are you doing? We spawn our camera in this case, right? Camera 3D what? Default. Our camera 3D in this case. That's the first thing we do. We spawn our camera, but we may also add our configurations. Remember the way we did our previous animations, like all of this. When we spawn our cameras here, not this, the sprite. When we spawn our camera, we just do camera to this, then we define the camera and all of those things. We can do the same thing for the 3D world. Literally, the only difference is that we change 2D to 3D, and we can still define the camera the same way we did here, and it still works. Like, literally still works. So that's the only thing that was done here. So we are going to stick with this. We can always modify it later, but showing you different patterns and different ways things have been done. That's what we are trying to do here. So we define the camera 3D with the default settings, nothing changes. Then we create a transformation. Transform what? From translation or from XYZ in this case. So we can use from translation also. From XYZ from translation. In this case, from translation, we require us to create the vector vectory, just like we did yesterday. Then create a new vector of X, Y, and Z plane. That's if you want to do something simple in this case, which is similar to this, it would be minus 2.5, 4.5, and 90. That's minus 2.5, 3.4.5, and 90, right? 9.0. What am I doing? So basically, this is what you're supposed to have if we were using that. Then looking at, because we are working with 3D now, right? And we're using this transformation. So we are saying looking at what? Looking at vector 3, 0, vector 3, y. You can see that it's looking at taking two vectors, vector 3. Look at it now. It's taking this self vector 3 and the up. Up is also into a directory for some reason, which is that vector 3 dot 0, vector 3 directory y is used instead. So let's just use that instead. So we can use directory dot y, which still makes sense. But in this case, we are using vector 3 0 and vector 3 y. So vec3 0. What am I writing? And vec3 y or dir y. I'm just using the the what was written there before to define it. So that 3y we give us the same as using vec3 0, if that is what we are using. In this case, we are not using vec3 0, so we use vec3 y. So what next? Okay, from XYZ is actually giving errors. The function takes two parameters. One parameter but two parameters were supplied. Where? How? From translation. Which function takes two parameters? Oh, from translation takes in. Yeah, that's what did I do anything different? Let me check. I'm mixing the syntax, literally the same thing. From translation vec3 dot new, yes, dot looking at. Am I doing anything wrong here? Do you guys see anything wrong different from what is here, like what is defined here? Because I feel like I'm using the same thing. Let me copy this again and change it here. So now I'll change it. Still the same. Okay, so I'm not going to use from translation, I'm use from XYZ. What is missing? Am I doing anything wrong here? Oh, jeez. I know the problem. Sorry, guys. Sorry for the mistake. Yeah, you can see the translation. It still does the same thing. Like I said, you can use XYZ. It's faster. You can use this. It works too. So we've spun our camera, right? The next thing we need to do is spawn our light source. That's how I like to start it. So the next thing is we spawn the light. Let's use the one that was defined, that was generated for me by AI, then compare it if that's what we want. So first thing is there's a transform here, but I prefer like to use the global transform first of all. So you look at the light the way it was defined. But in this case, we have the point light, which is what is being used. But in this case, this doesn't define the point light. So we use the point light in this case, and we define define it. In this case, we can use point light or default, right? Without configuring it like this. But want shadows to be enabled. So is shadow going to be enabled by default? We can check that out. And we can transform it by defining where the light is going to appear from, like this, right? By defining it to be appear at the top, 5 upward x00. That's it's going to be like in the middle of the word. I just want to leave it like this so you see the changes. And we're going to make it to look like this. Actually, you can see they also transform this 4, 8, 4. That means 4 to the right, 8 upward, 4 on the z axis also. But I'm going to leave it based on what we have here, 050 for now. So after spawning the lights, let's spawn the next thing. What do we have next? We have the cube, then the base. So let's start with the cube, then the base. So in this place, I'm going to spawn the cube. And what do we have for the cube? Let's see what we have first. For the cube, we need to define a mesh, right? We understand we need the mesh because that's what we need. So we are going to define a mesh 3D, first of all. We are going to define meshes.add. We are adding what? A cuboid in this case. So we are adding our cuboid and defining the sizes of our cuboid and other things also. So our cuboid has what? So our keyboard contains the dimension. Let's use the one here, which is 1.0, 1.0, 1.0. The reason why this is 3 is because now you understand, like I said, when we're dealing with two shapes, with 2D shapes, we use the length and the, so let's just say the width and the height, right? Width and the height for 2D shapes. Now we have that's between the X and Y axis. So let me explain using this analogy, just to draw something. So when we work with 2D shape, working with things like this, right? Let me use this color. This is a 2D shape. We have the x-axis. This is literally the x-axis. This is the x-axis. Let me increase the size. This is the x-axis. We have our x-axis here. Keep making mistake. This is our x-axis, right? So let me put it here as our x-axis, and then this is our y-axis here. So we have our y-axis. Let me just call it y-axis and x-axis. So whenever we work with anything here, basically we are working with x-axis. This is our x-axis, and this is our y-axis. Let me just put it like this, right? But in this case now, because there's no z, but the moment we start working with 3D shapes, which this cannot allow me create, but the idea is that we have another one called the z-axis, and the z-axis is somewhere here. It's going to be, so if in a 3D world, it's going to be somewhere. No, currently this is y and y, right? This is x and x. But where does the z come? Z comes behind it, kind of like behind it in this form. And then you have something like this. So how do I know it is z? If I want to define or draw a cuboid, how do I do it? I define something like this, right? So what I do is I duplicate this and I add it in front of this. Now, do you understand what we just did now? Bring to front. Now, do you understand how definition comes to be now? So this is my z. So you can see my x and my x still remains where it is, right? But this is my z axis. So if I'm defining anything now, this is my x, this is my y, this is my z. So if I'm to make use of this, this is still my x axis, this is still my, no, where did you go to? This is still my x axis, right? Defined here. This is my y, defined here, and this is my z. So in a 3D world, if you look at it, see the way we converted it 2D shape to my 3D shape. So automatically and essentially this is how it works. So this translates from a 2D shape to a 3D shape. So that means if we want to talk about it, rendering that particular sprite we just did, which is this guy, that's why they are just 2D, because you can only see everything on one plane, just like we see the light here. It seems like it's on the same plane. But because if I translate it to a 3D implementation, it simply means that I can now bring the light a bit forward. So I don't have to give the illusion of perspective like I'm doing with the sizing again. I can actually push it either inside, in between this space, in between the length of this arrow from here to here. I can define anything on an infinite manner, because the distance between them is, though it's not infinite, but then I can create it in a range value to give it perception of depth. So that's the difference between the 2D and 3D. So in 2D, we need just X and Y, but in 3D, for us to create the 3D, we need Z. And that's why I was able to create the Z and create the 2D to form that 3D shape and to make it work. So that's basically what we've done. So now going back to this implementation, or going back to the explanation from here, now let's complete our cube, right? Now we understand why we created our cuboid like this. We need to also transform the cuboid, right? We want to position it somewhere in our world. So we need to create a transform. We need to create a transform also. And from where we want to translate it, we can use from XYZ also instead. So let's use from XYZ here. So we're going to create a vector. So we can use XYZ and create something like this, which is perfect for what is here. Then we can create a material 3D. Now the reason for material 3D is because we want it to have a color, but the color we can define cannot be the same as we define for a 2D, right? We can't use it to define for something for like a 2D implementation. We need to define it for something like a 3D implementation, which is like a mesh. So in this case, we do something like this: mesh material 3D. In this case, now the mesh material 3D is just going to be something similar to the way we define our mesh material for our bloom. Remember the mesh material, which is this one. We define the material and then we added the color to it. But in this case, we need to define the materials also that we already defined here, this one, and then we add our colors to it also. But in just the same way we add our colors here, which is color RSGB, right? We can do the same thing here. I just copied and pasted it here and it still works if you look at it this way. So we have the same thing. So in this case, we want the colors to be different. No, we want the color to be the same, because I copied the color I copied from here is that of the hexagon, which gave us that light green effect. If you remember from yesterday's one, it gave us that light green effect. I can define a cube with another color, which give us this deep blue that they used here. But I want us to use the one with the light green to change our own a bit, right? Then let's implement the circular base now. Circular base, which is this light gray implementation. Remember, there's a shadow here. I remember we defined our shadow too, that it should have shadow. We defined that somewhere. Shadow enabled. Okay, we've not done that, but we assume it's part of the default point light that we created here. The point light is just the kind of implementation that I did here that is simulated with this one. That's what the point light is. This that I did here, trying to simulate this light effect. But you see, there's no shadow, so that doesn't happen. But in this case, we are creating a point light now because we are working with 3D, right? We can create a point light here and make that work. But in this case, because I'm working with 2D, I couldn't create a point light, so I had to simulate it with a shape and the light source. That makes sense. So now let's go back to this and let's complete our circular base, right? So with circular base, I can just create it since I know that it's just going to be a, okay, you know what? Let's still write it. So spawn the circular base. So for this, I'm going to create a command.spawn, and I'm going to create double of this, but I'm going to have the column first. I hate having that issues. So I'm going to create a mesh 3D, basically the same. No, I want to write it. So I'm going to create a mesh 3D, right? Meshes.add. I'm going to create a circle. I'm going to create it as 1.0. That's the radius, right? I'm creating a circle already. So the next thing I'm going to create is a mesh material 3D. Remember, we need the materials to define the colors and other properties on it. Now remember, it's not just colors we can add to it, you can add textures to it also. So sRGB, we can define the color, but the color in this case is gray, so I'm not going to use the same color as that green color. So I'll look for the gray color that is actually being used here, and I'll call it color of white. So that even makes more sense. So I just call it color of white. So white. And the last thing is what we want to define here, which is our transform from, nope, we're not using transform, right? Because we can use transform, but that's not the intention currently. We want to use the quart because we want it to rotate, right? We want to use the quart, even if it's not going to rotate, we want it to have this feel because this is a 3D scene, right? So in this 3D scene now, what can we do here? We can't move it, we can't click it, we can't drag it, we can't do anything. It's just there. You can see, but it's there. So, but what we want to do is we want to create a rotation, a shape, a 3D shape, right? So what we want to do is we want to transform it like this. So we are going to use the from rotation. So from rotation quart. Remember we used quart yesterday when we were working with when we were trying to implement the rotation first of all for our shapes. That's like the rectangle we created yesterday. We implemented the quart at first. We talked about quart yesterday and we said this was let me see. Let me just define it. We'll come back to that. From rotation X, in this case it is X, not Z. So if it was rotation Z, it will rotate along the Z axis, kind of like instead of rotating. Let me define what it was going to be. So this is it currently. This is a 2D shape, right? If it was defined along the Z axis, okay, let's say this is an oval. There's no way I can show you this in a 3D plane because there's no 3D plane for this. It's just 2D. But the difference is rotating it along the Z axis now. I can do this to it. How do I rotate this? It's quite impossible to rotate this. It's extremely impossible to rotate this. Oh, sheesh. Oh, jeez. All right, so I can't explain using this. So I'll just try to explain it with the implementation itself. So I'm going to copy this. I don't need to write this. Okay, which is literally the same thing I did for us. Minus. So this is a negative STD. So I'm going to use that minus standard F32 constant fraction pi 2. So let's do this. This is basically our 3D is our 3D world basically. So let's run this. I'm going to first add it to our main, the actual main. I'm going to run scene 3D dot main. I'm going to make it public. Let's go back to our scene 3D, make the main public, and that way you can use it and go back and there's no more error. And then once we run this, it's going to run the 3D scene first. I'm not going to comment that out. Just interestingly, we can't run both of them at the same time. If we can, I will have just left both running at the same time, but we can't run 12 the instances. Well, I don't want to run 12 the instances. There's a way to bypass it, but then just see the 3D. So we see the 3D cuboid created here, as you can see. So it doesn't currently show the, why is it showing? Okay, this is the green color for what we showed yesterday actually, but it doesn't show the base. Why does it not show the base? I need to check that out. Something is wrong. Did we implement something wrong here? Did we do something? Did we do any wrong thing? There are no errors basically, so everything should be fine. Oh, yeah. Okay, now you see the base, but it seems very small compared to what we see here, isn't it? So we need to do something. The circle here is, oh, it's 4. I created the circle of radius of 1. So remember, that's why. So it's perfectly understandable. The radius I created that circle of 1, so it's perfectly understandable. So we can make it 4. And yeah, let me go back to the quad. I mentioned the quad yesterday, right? A quantum representing an orientation. So how do I explain quantum? Okay, there's no way for me to explain this right now, but just know that it represents an orientation. Orientation in this case is more like a circular orientation, right? So you can read all of this here. The container is intended to be of unit length, but may denormalize due to floating point errors, creep, which can occur when successful container operations are applied. CSIMDB vector types are used for storage on supported platforms. So all right, so let's just leave this for now. But just know that it's mainly used for rotation like this, right? To implement something like that. So to proceed, I'm going to rerun this so that the radius becomes a bit bigger, and I'm going to also scale up. So the transformation for the cube, right, is different from what transformation for the light source, right? Comparing our own light source to theirs, you can see theirs start from 484, right? Even though the camera is the same. We use the same transformation for the camera. Am I correct? Yes. We used the same. The cube is literally the same dimensions except for the colors. We used our own colors for the cube, which is different. We used from sRGB, right? Which is this, and this, which is not the deep green color, but the other things are the same. And then we spawned the cube on the same dimension. The light is the only thing that is not the same because we didn't define the transformation for the light. We only assume the default. So if you want to check now, you can see the default based on the light. There are literally no shadows, but let's not conclude for now. Let's refresh this. Comparing that to what we have here, you can see there's a shadow on the cube, and here is brighter than here. So that means the light source is somewhere. Now we have something similar, right? We have almost similar implementations. But that's the difference. Look at the difference here. The difference is there are no shadows on this because we did not define shadows, right? And that's one. Secondly, even though the circle remains literally they are very similar. The cube similar, the circle similar, difference in color here, but the circle same color, the cubes have different color, and the light source gives this more like a 3D feel, more like a light is reflecting on this. This still looks like a 2D kind of plane, even though it's not 2D. We can't implement this in 2D, but it doesn't give that actual perception of 3D in a very, if you think about it, it doesn't really give that. But we want it to give that. We definitely want it to give that. So we need to now go use the definition that was defined here for the point light. So I'm going to do that. I'm going to define the point light here, and I'm going to define it like this. And the shadow enable true. I'm going to define the shadow and what again? The default, right? Shadow enable true and default like this. The other things we can define, let's play around with it. We can define the color of the shadow. We can define the intensity of the light. Just like, remember when we did that for, okay, I've cancelled that, but for the sprite animation, for the sprites, remember, I was able to use the bloom for that. Remember when I did that and I was able to do this intensity for the bloom. Where's that? Where's it? For this. Remember we did the intensity for the bloom. We did the unwrap and we did the intensity on it. And then we could also increase the intensity. I wanted to do that, but because we don't want to, like, we can't pass by value, we can only pass by reference to prevent ownership from the bloom. I didn't do that eventually. So but then it's the same concept here. We can increase intensity and the color. In this case now the color, you can also change the color to color the white, but in this case you can use yellow. I don't know if there's yellow, but I didn't think there's amber. Nope. Which colors exist actually? Let me see if there's like default colors that exist that we can use. Here's amber. Hmm. So what exists in color? Let's check. Let's check. White, black. So this is actually the color library. There's white, black, and none. Oh, so there's no colors defined for yellow and stuff. All right. So if there's no color defined for yellow, we can define it. Remember, we can do that. You can do that using the same one we use for the bloom. So let's go back to the sprite animation. Define the color we use for the bloom. Let's go back to the spawn where we define the colors for the circle. We define this color for the bloom, this, and this was what we used. So we can do the same thing for this, right? This becomes the color. But before I do this, I want us to see that it actually looks like what they defined, since we are using the actual configuration, except for the transform. Which, you know what? Let's implement the transform. Don't let us make it look weird. Let's make it look a bit more reasonable. Let's increase this by 8. If I'm going to do this, I'm going to remove this, use the point light like default again, just the same way we have it before, just the same way we had it prior to now. I'm going to make this 80, not 8. In their own case, they use 484. Okay, you know what? Let's just use the same light configuration they used first. Then we tweak it, we change it, and see the results also. So let's do that. I'm going to rerun this. Now it's making sense, even though there's no shadow, but you can see that the colors changed. Now that's because of the light source. Now there's no shadow yet, yes, but because we took it to look like the light direction, you can see that it looks, this place, the right side is brighter than the left side, right? So it's similar to this, the right side here is brighter than the left side. So if you see it now, it has similar light sources based on what we've defined. So we can make a change to it. We can make changes. The changes we want to make now is to give it, enable shadows on it. So I'm going to leave the same light configuration. I'm going to just change this. The point light, I'm going to enable shadow. That's the only thing I'm going to change. So let's see if it gives us the same feel as what we have here. Definitely it should. So let's see. Now we have the shadow. Finally, we have the shadow. And so, yes, we've done all of this. And finally, we have something similar to what is here. We've implemented our first 3D component using Bevy, and it makes a lot of sense. Yes, congrats to every one of us, myself included. We've implemented this 3D approach. And we now see how it works. So all these 3D implementations you see, if you see these with light sources and all of these things, you can see it here being implemented, perfectly implemented, 3D and this and that, and it works. Right. Okay. So now that we've done this, what's the next thing we can implement here? Okay, so let's change the let's do the last thing we wanted to do, which is the intensity. Let's start with the intensity. I want us to see the changes as we tweak the light sources little by little by little. So let's change the light source and see the intensity and see what changes. Now you can see the intensity of the light actually reduces, in the sense that we no longer see the shadow anymore. Everything becomes dark, literally dark. So all we need to do is to reduce intensity. I'm going to just make it like let's see. Let's make it 10. Right, so I'm going to run it again. Let's see what we get. Oh, I think I understand why. The intensity might just be from 0 to 1, and I'm adding high values to it. Why is AI suggesting this nonsense for me? So let's make it 0. 8. Let's see if it works. Let me make it 5. Let's see if it works. I'm going to run it again. And if it doesn't work now, probably because the intensity is not an actual configuration. So we are going to remove it. We're going to assume it doesn't exist here. So we're going to remove the intensity, use the color. So let's find the color to see if it changes. Yes, it works. So you can see the color now. You can see that it gives this yellowish light kind of feel to it. That's like a sunlight kind of feel because it is actually very bright. It's way brighter than what we have there. So that's because of the color we used. So you can also change the color to something like bluish color, does the same thing. And you can see it gives that feel. So we successfully created the whole first 3D render, which is perfect in this use case. With shadows and everything. So successfully did everything we wanted to do today, which is the sprite animation and the 3D rendering. I've already done that. So we have a 3D scene, a 3D rendering. We have the sprite animation successfully done, and everything is done in Rust from start to finish. No other language. So I hope this gives you a feel of how to implement this using just normal basic structures to combine all of these things to make it work. Of course, Bevy is doing the heavy lifting for us, but it still works. It still makes sense, right? Implementing this still makes sense. So we can remove the color because that color is too bright, even for me. And then we can remove the global transformations too, and then try to see what we have eventually. So trying this out again, what do we get this? The light is soft. We get a soft. We get something similar to what was implemented here. Very soft light, and you can see that it's not difficult to make. What we need to do first of all is define the light source or define the camera first, like the 3D camera. Define the light source on it. Define the position of the light source. If we want to do it, we can make it. The light source is coming to the right, but we can make it start from the left here. So let's try doing that to see. So we define the light source here. Where is it? Here, right? So we can make it -4. That's the x-axis. Transform it to the x-axis, and then we just define that. So let's do that again. Let's see. So let me run this again. Change that. So that way the light source should be reversed. It should not show from the
It's
right
19
side,
hours.
but from the left side this time around. Now you can see. Instead of the shadow being here, the shadow is now here, simply because we've shifted the light source. So does that make sense, right? So we are still going to be doing other things like playing around with the object, right? We are going to be doing that. And what we are going to be doing is we can interact with the objects, like moving them around, clicking them, dragging them, moving them, playing with the camera, rotating the camera so we can see the movement. We can see everything in 3D space. Like we are going to implement rotating the camera. That will be one of the first things we do in our next series, which will be like tomorrow. It will be done in like 3 hours time. So if you're not subscribed, just click the subscribe button so that you can get notified about when that drops. It's going to drop in a few hours time. It's going to be the same time. So yes, like 4 p.m. But still, it will be good if you are notified so you don't miss it. And after doing that, we are going to make sure that you can rotate the entire thing. Let me show you an example of what we are going to do tomorrow, just to give you a feel of it. Where is this? Okay, I'm going to take this back to examples. So this was the 3D, right? So what we are going to do is we are going to implement this. The camera viewport to world. We are going to implement this. See, these are 3D shapes you can build. We can see all of this with their shadows cast on all of them. And you can see the shadows. You don't need to do anything to implement shadows. All you need to do is just define it and say, yes, I want this to cast shadows. And it does that. We can see how to implement other things like this, where you can move, no, not custom mesh, but where you can see different light maps, different lighting conditions, and like you can actually move the world like something like this. We're going to implement all of this using the same Bevy and Rust. We're going to do that. We're going to implement all of this also. The spotlight, where you can move the light, you can move the world itself, you can move anything within this 3D world. We are going to see all of these things before we proceed into actually building games. right? Now we are not going to work on all of them at once because yes, we don't have all the time. Except if someone wants it, then you request for an actual course, then I can create this as a course because it makes actual sense. But then for now, this is just a way to get started with it and for you to learn how to work with Rust. Rust is not hard, right? So what we are going to do is something similar to this. Let me show you an example. Mhm. Let me show you this viewport to Word. What we are going to be implementing next. Let that render. Probably take a bit more time because it's rendering on the web. You need to do the cross compilation first. But you can see it's not really that difficult to do too because it's just few lines. Few lines. All you need to do is to implement your setup for the camera, light, and plane. Once you implement the plane, which is just the ground, and the ground basically is just a structure you define, and then you draw your cursor on it, which is more like your word. It's taking a bit more time. Okay, so while that is loading, let me show you guys another one. Okay, yeah, remember the 2D bloom we did, right? Let me show you an example of 3D bloom. Now, this is just an example of what to come, just to give you that appetite of, oh, yeah, we can do this. This is possible. Now, if you can implement something like this, like what we've done today, that's starting to 3D implementations. It's not difficult to do. It's the same thing as writing a web page, whereby you start with a single page, then you create multiple pages, you render a button, you render a card, you render an image, put the image into the card. Do you understand the step-by-step approach? It's the same thing. All you need to do is create a file, import this, create the logic. You use the AI to create the logic. We've not even used the AI to create anything, but we are going to when we start building actual implementations. But for now, we need to understand the foundational knowledge. We need to have the foundational knowledge, understand the foundation of building in 3D and in 2D and using Rust and building games also. So once you understand all of these simple things, then we can implement more advanced concepts. Okay, for some reason, this is not loading any of them. Weird. I wanted to really show you guys how to move all of those things. Wow. Okay. Still not loading. But then I think I'll just show you guys what we need to do since it's refusing to load. Then we'll pick that tomorrow. Just like we decided to do three things today, and we're able to do the three, this animation, the sprite sheet, and we're able to work with the 3D scene. We render the scene in 3D, we saw the shadow, we rendered a cube on top of a circle. So one thing we can do is let me show you guys one thing before we stop, before we round up for today. Currently, this is what we have. We have the cube on the image, on the circle, on the round flat plane, right? And we can do one more thing. We can animate the cube by transforming it to, let me say 2.5. I want it to fly up a bit. So you have the illusion that it is floating, or it is being elevated, right? Or it is flying. Let's give it that feel. Nice. Now you see what they've done here. So this is basically what I wanted us to see. But it's a bit too much. Let me make it 1.5 or just 1 itself. And let me run this again. And it gives that illusion that it's floating. You can see. And even with the fact that it's floating, you can see that the light source still reflects on that. It still casted the shadow completely from the top because that's where we define the shadow to be, the light source to be rather. So the light source automatically gives the shadow to it without we doing anything. All we needed to do was just defining shadow enabled to be true, and that's it. That's literally everything we did. We can also define the depth bias, the affect light diffuse. We don't need all of this now, but we can see that it's possible. There are other things we can do. Soft shadows enabled. Yes. All of those things perfectly defined for us. So we see, right? So this is it. This is basically what we are trying to do and what we've been able to implement today. So I hope you guys have learned something. I hope you guys have really learned how to get started with 3D game development, 2D rendering, animations, 3D rendering on scenes, and Rust actually, because like I showed you guys in the 3 days now in part one, and part three of this build a game with Rust or learn Rust by building a game series, you can see that it's not difficult to actually pick up Rust, even if you're a total beginner, right? I know we don't talk about Rust much, but by talking about the game, something that is exciting to see, it can spark your interest. And you can see that by doing it, you can actually even read the code. I believe that this is as simple as possible for you. You understand what this is. If you follow the for 3 days, followed everything we've done in 3 days now, you can actually pick this up and implement it, right? You can. And then if you also want to, if you also have followed what we've done so far, you can also understand that what you need to do is to spawn this. So by writing this yourself, you are already writing Rust. You are literally writing Rust the same way someone that's been writing it for 2 years writes it. There's nothing different as long as you understand that, okay, when I want to transform, I write my transform, I use double semicolon to call a function that is defined. That means transform is a struct, right? And this is a function defined on the struct, and the function takes in a parameter which is passed as an argument here of a vector 3. Why vector 3? Because I want to create a vector, right, and make use of it. That means I need the XYZ for to be able to transform the actual entity that this transform is defined on. So that means you're already understanding it. So if you are writing it, you know that the first thing you want to do for yourself, if you are writing this, representing it, is to write a struct, call it a transform, define it like this. I'm just giving you an instance now of what you can do. I'll call it, in fact, let me remove it like this. I'll call it transform like this. And inside the transform, I have a from translation, right, like this. Inside of it, I can have a new if I need a new, just the same way I showed you guys the other time, right? So just the same way, let me show you what I'm talking about because I don't want to write all of this. But then you can see just the same way we defined this, our struct, and then we implemented it. So we can just do the new, we can define this here without this the struct is going to be like our implementation, our definition of what we want to do, right? Without implementing it. And then we can just define our struct like this, and then define our implementation for struct or transform just the same way we have here. Do you understand it now? And if when you define this, you can see from this, from this, from this. The reason why we have this is because we can now call transform like this. You can see if I click on this, it takes me to this one, this transform, and then we can now have other things inside, like what we need. Like the other things we can use from XYZ from rotation, we can define what we want to use with it. Like in this case, you can see this automatically defines vec3 as the parameter that is going to be used. And then I can decide to say v dot something works automatically. Do you understand it? So this is basically how to write your Rust. You are not, this is not me writing the entire Rust syntax, right? But then it gives you an idea of if I see this, I understand it is being written. If I see this, I understand this is a struct. Automatically understands the struct. All that means is something like this. Point light. And to show you that it works, I'm going to create a custom point light, right? I'm going to create shadows enabled bool. I'm going to create something else, color this. I'm going to create intensity this. I'm going to create one more thing, radius. Let me do this for now. And then just this. So if I want to use it here, look at what's going to happen. Custom point light, right? Automatically. So if I want to use it here, I'm just going to do this. Yes, I know it's not implemented for it, so I can't use it inside of this. So if I wanted to use it inside, right, all I need to do is just define it like this. I know that there's no initializer for any of these things, right? Because if why is complaining is because I need to define, I need to implement this. If actually want to use it for this component, to use it inside there, I need to implement component for custom point light to be able to use it inside of this place. So if I do it this way now, it should not give me an error here anymore because I need to implement the initializer, right? So what that means is that if I want to implement it, I need to implement other things, but I don't want to implement component for this. I just want to implement custom point light. So that means I bring this one out here, and then I implement all of these things, meaning I need to implement shadow like this, just the same way we have this, right? I implement a function called new. I implement a function for whatever it is I want to do, something like this, and I implement the if I want a function on it like return return, let me use the actual light position. This can be a function that I have, right? This is extremely possible. This is just an instance. It's not a it's not an actual code. Like this is an actual code. What I'm writing here is not an actual code. Just don't take it as it is. Don't just take it as it is, but it's not actual code. Right? I'm just showing you what we can do. So in this case, this becomes this. This is going to throw an error because it's telling me mismatch types, blah blah blah, whatever. Because I'm not returning anything from here. I can actually return self dots. Okay. I can return self dots. Let me call this is shadow enabled. Self dots shadow enabled. I'll just return this. But basically, because this I'll return this as a bool, and now automatically this becomes um except if I'm going to make a reference of self from here, which I don't want to do. Okay, but then something similar to this one, which is FPS of here, which is what we pass here, blah 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 here, and then you have access to it and you pass it here, you use it here, automatically return this to something similar to that. But in this case, what I'm just trying to show you is that you can have something like that, just like you have something like this here, right? You return an instance of self here, also custom points self. Self means custom points, just to clarify that. Then we can have an instance of self, which we can define as I can actually define self here. Self as a reference to self, if I'm not mistaken. And then I create self. Self should give me self shadow enable. You can see. So automatically this means I've defined this. I can have the same for I don't need the return since that's it. I don't need the return since that's the only thing, right? I can just do this. Except if I'm using return, I have to use the closing bracket again. But since I don't need that, I can just do this and everything works. No, like this. And then I can define another one called set shadow enabled, just like this. You can see that it literally makes sense, right? So this is if I want to implement the custom point light now, what I need to do is I need to define this as my initializer, or I can do this. I can initialize this now, which is my initializer for this new custom point light. Dot new. No, something is missing. New. What am I missing? Let me see this one. Oh, I didn't pass anything to it. Yeah. So then I didn't pass anything to it because I'm not passing anything to it here, but it's just defined by default. In this case, I'm actually defining this and passing it as a parameter. So if I'm to do that, I have to define the new. But in this case, I'm not doing that. So what is actually happening here is here's the definition. Implementing this, I can move this out of this place. And if I want to use it outside of this place, I can just set it up somewhere here and custom point here, custom point light. You get the idea, right? We are not implementing it because we don't actually need it. We need to define it inside the function to use or something. But because we can't use it directly inside there, dot new, you can see the functions we define. New set shadow enabled is shadow enabled. So we can use the new to define an instance of it. All right, or we can create something like this. You can see it literally the same thing as point light was done here. But remember, we don't have the default setting defined, so we don't have that defined there, so we can't use it. Right? But it's going to complain of something. It's going to say missing fields, initializer, this. Why? Because we don't have the shadows and all of the other initializers defined, which is what we need to have like this. So if you define it like this, you can see similar to the point light. So by learning this already, you know that by writing, you can write your own ROS literally by understanding how this works. So you're literally writing custom point light and you're also defining point light here. Like nothing too crazy. So if you see things like this, you can look at the code base and understand what is happening. This is just a struct. Whenever you see something like this, is a struct. Whenever you see something like this, is a struct. It's just a struct definition that was merged and combined into something, something, something. This way, if I want to define it, instead of defining it like this, I can also use the new keyword and define everything like this. Still the same thing literally. Because all I need to do is define my shadow enabled. Let me remove this. I need to define it, but there's no argument passed. The reason why there is no is because I didn't define any parameter for new, right? But anytime I'm doing it like this, I want to define it. I need to define all the fields, radius, all of those things, just like we did just now before I removed it, like this. So this is it. So by this doing this now, you've already instantiated this new structure created. But we don't need this. I'm just showing you that everything we are doing right here is showing you, is teaching you how to implement Rust, even if you have no prior knowledge. Why? Because we are using almost everything that you would do in an actual Rust project. We are implementing it by writing this game. So you should put your mind to it. You should learn. You should be able to learn. You should be able to get confident working with Rust by following it. And so that's why I said, if you have someone that also wants to learn, don't just think of it that, oh, this is game development. I'm using this to actually give you a pointer to real life tasks, because this is something you probably see in a real life scenario. You won't see something simple. You'll be seeing something like an actual library that has been prepared, an actual framework that has been already documented, written, that is being used in production, or that is about to be used in production. That's what you'll be jumping into, except you are trying to build your own from scratch. But then you don't need to. Just the same way we've done all of this. So this is literally what we are implementing today. I'm going to stop here for today. And like I said, for you to get notified for the next class, for the next series, next episode in this series, you need to get subscribed. So I really appreciate if you get subscribed, get notified, so that you can be notified when it happens next. And whoever you are sharing it with, also tell them so that they can be notified, right? So that we can move on, because tomorrow we are starting with the 3D again, and then we are moving ahead. And like I said, we are progressively moving. We started initially with understanding ACS. Then in part 2, we started with creating meshes, worked with colors, translations, transitions, transformations, literally. And today we've done 2 things, animations and 3D. Tomorrow we are going to go into something much more advanced. So, and you don't want to miss it. So that'll be all for today. Thank you so much, you guys, for joining. Really appreciate your time, giving your time to learn, because it is important. Yes, I know I'm the one thanking you for it, but it is important for us to learn together. So thank you for taking your time to learn. Thank you for giving your time to do this. And hope you've learned something from today's video, right? If you have any questions, feel free to drop your comments and your questions. I will be answering those questions as much as I see them, right? I'll be answering any question I see. So feel free to drop any question, no matter what it is. And if you need to reach out to me personally, you can send me a mail, or literally I'll drop my info on the on the description of this, so that you can message me directly if you have questions, and then we can pick up from there. So yeah, that'll be all for today. And we'll do this again tomorrow. Same time. See you guys. Bye for now.